statistics, when piopolysedniel to get a piobarbit function, of a probability density function where it lacks the unsholfetui of a piobarbity. Density functium nom of the pit of being positive. Asterisk I110m the pragmity. There except via on. Emicrosiopic object. Point of view nothing cmb slid about the world out. Concepts however even within the world of OM-con. CCPTS putides do not seem to have an independent existence. They are represented in theory on of by wave functions, and the meaning of the wave function lies only in iolati, ns of other, may show c, pick, things. Like a table or a chan have certain nect experimental metylings tint is we agams out sensory experiences directly in terms of them. These experiences are such that we can believe that these objects have a pi system existence and well-defined locality, n in space-time that is logically independent of either things any, nevertheless the concept of independent existence evaporates when we go to wn to the level of putiles. This limitation of the semakept of mdiptulant entit / the level of particles emphasizes according to the pragmatic view that even tables and chans are for us to ls to correlating. Expel ICNE 72 / patterns of organic energy. Quantum mechanics is based on the development in isolation of an observed system. Development in isolation refers to the isolation that we create by separating the region of preparation from the region of measurement. We call this situation isolation, but in reality, nothing is completely isolated, except, perhaps the universe as a whole. What would it be isolated from? One asterisk. The isolation that we create is an idealization, and one point of view is that quantum mechanics allows us to idealize a photon from the fundamental unbroken so that we can study it. In fact, a photon seems to become isolated from the fundamental unbroken because we are studying it. Photons do not exist by themselves. All that exists BV itself is an unbroken wholeness that presents itself to us as webs. More patterns of relations. Individual entities are idealizations which are correlations made by us. In short, the physical world, according to quantum mechanics, ICS, is not a structure built out or independently existing unanalyzable entities, but rather a web of relationships between elements whose meanings arise wholly from their relationships to the whole. Step 4. The new physics sounds very much like old Eastern mysticism. What happens between the region of preparation and the region of measurement is a dynamic, changing with time, unfolding of possibilities that occurs according to the Schrödinger wave equation we can determine for an moment. In the development of these possibilities, the probability of any one of them occurring. One possibility may be that the photon will land in region A. Another possibility may be that the photon will land in region B. However, it is not possible for the same photon to land in region A and in region B at the same time. When one of these possibilities is actualized, the probability that the other one will occur at the same time becomes zero. How do we cause a possibility to become an actuality? We make a measurement. Making a measurement interferes with the development of these possibilities. In other words, what happens /73? Making a measurement interferes with the development in isolation of the observed system. When we interfere with the development in isolation of the observed system, which is What Schrödinger's wave equation governs, we actualize one of the several potentialities that were a part of the observed system while it was in isolation. For example, as soon as we detect the photon in region A, the possibility that it is in region B, or any place else, becomes nil. The development of possibilities that takes place between the region of preparation and the region of measurement is represented by a particular kind of mathematical entity phys. Physicists call this mathematical entity a wave function because it looks, mathematically, like a development of waves which constantly change and proliferate. In a nutshell, the Schrödinger wave equation governs the development in isolation, between the region of preparation and the region of measurement, of the observed system, a photon in this case, which is represented mathematically by a wave function. A wave function is a mathematical fiction that represents all the possibilities that can happen to an observed system when it interacts with an observing system, a measuring device. The form of the wave function of an observed system can be calculated via the Schrödinger wave equation for any moment between the time the observed system leaves the region of preparation and the time that it interacts with the observing system. Once the wave function is calculated, we can perform a simple mathematical operation on it, square its amplitude, to create a second mathematical entity called a probability function, or, technically, a probability density function. The probability function tells us the probabilities at a given time, s, of each of the possibilities represented by the wave function. The wave function is calculated with the Schrödinger wave equation. It deals with possibilities. The probability function is based upon the wave function. It deals with probabilities. There is a difference between possible and probable. Some things may be possible, but not very probable, like snow falling in the summer, except in Antarctica where it is both possible and probable. The wave function of an observed system is a mathematical catalogue which gives a physical description of those things which could happen to the observed system when we make a 74 patterns of organic energy measurement on it. The probability function gives the probabilities of those events actually happening. It says, these are the odds that this or that will happen. Before we interfere with the development in isolation of an observed system, it continues to generate possibilities in accordance with the Schrödinger wave equation. As soon as we make a measurement, however, look to see what is happening, the probability of all the possibilities, except one, becomes 0, and the probability of that possibility becomes 1, which means that it happens. The development of the wave function, possibilities, follows an unvarying determinism. We calculate this development BV using the Schrödinger wave equation, since the probability function is based upon the wave function. The probabilities of possible happenings also develop deterministically via the Schrödinger wave equation. This is why we can predict accurately the probability of an event but not the event itself. We can calculate the probability of a desired result, but when we make a measurement, that result may or may not be the one that we get. The photon may land in region B or it may land in region A. Which possibility becomes reality is, according to quantum theory, a matter of chance. Now back to the double-slit experiment. We cannot predict where a photon in a double-slit experiment will land. However, we can calculate where it is most likely to land. Where it is next likely to land, and so on. This is how it happens. Suppose that we place a photon detector at slit 1 and another photon detector at slit 2. Now we emit photons from the light source. Sooner or later one of them will go through one slit or the other. There are two possibilities for that photon. It can go through slit 1 and detector 1 will fire, or it can go through slit 2 and detector 2 will fire. Each of these possibilities is included in the wave function of that photon. Let us say that when we examine the detectors we find that detector 2 has fired. As soon as we know this, we also know that the photon did not go through slit 1. That possibility *v we in predict is the probability corresponding to specification that sin be mapped into a density function. Accurately speaking, we do not calculate probabilities at points but Lorentz transition probabilities between two states. Initial preparation, final detection, TAC, of which is represented b\a continue as function of x and p, position with momentum. What happens /75 no longer exists, and therefore, the wave function of the photon has changed. The graphic representation, picture, of the wave function of the photon before we made the measurement had two humps. In it, one of the humps represented the possibility of the photon passing through slit 1 and detector 1 firing. The other hump represented the possibility of the photon passing through slit 2 and detector 2 firing. When the photon was detected passing through slit 2, the possibility that it would go through slit 1 ceased to exist. When that happened, the hump in the graphic representation of the wave function representing that possibility changed to a straight line. This phenomenon is called the collapse of the wave function. Physicists speak as if the wave function exhibits two very different modes of development. The first is a smooth and dynamic development which we can predict because it follows the Schrödinger wave equation. The second is abrupt and discontinuous. That word again, this mode of development is the collapse of the wave function. Which part of the wave function collapses is a matter of chance. The transition from the first mode to the second mode is called a quantum jump. The quantum jump is not a dance, it is the abrupt collapse of all the developing aspects of the wave function except the one that actualizes the mathematical representation of the observed system. Literally leaps from one situation to another, with no apparent development between the two. In a quantum mechanical experiment, the observed system, traveling undisturbed between the region of preparation and the region of measurement, develops according to the Schrödinger wave equation. During this time, all of the allowed things that could happen to it unfold as a d/eloping wave function. However, as soon as it interacts with a measuring device, the observing system, one of those possibilities actualizes and the rest cease to exist. The quantum leap is from a multifaceted potentiality to a single actuality. The quantum leap is also a leap from a reality with a theoretically infinite number of dimensions into a reality which has only three. This is because the wave function of the observed system, before it is observed, proliferates in many mathematical dimensions. Take the wave function of our photon in the double-slit experiment for example. It contains two possibilities. The first, 76 patterns of organic energy possibility, is that the photon will go through slit 1 and detector 1 will fire, and the second possibility is that the photon will go through slit 2 and detector 2 will fire. Each of these possibilities, alone, would be represented by a wave function that exists in 3 dimensions and a time. This is because our reality has 3 dimensions, length, width, and depth, along with time. If we want to describe a physical event accurately, we must say where it happened and when. To describe where something happens requires 3 coordinates. Suppose that I want to give directions to an invisible balloon floating in an empty room. I could say, for example, starting in a certain corner, go 5 feet along a certain wall. 1 dimension, 4 feet directly out from the wall, 2nd dimension, and 3 feet up from the floor, 3rd dimension. Every possibility exists in 3 dimensions and has a time. If the wave function represents possibilities associated with 2 different particles, then that wave function exists in 6 dimensions, 3 for each particle. If the wave function represents the possibilities associated with 12 particles, then that wave function exists in 36 dimensions*. This is impossible to visualize since our experience is limited to 3 dimensions non-theless. This is the mathematics of the situation. The point to think about is that when we make a measurement in a quantum mechanical experiment, when the observed system interacts with the observing system, we reduce a multidimensional reality to a 3-dimensional reality compatible with our experience. If we calculate a wave function for possible photon detection at 4 different points, that wave function is a mathematical reality in which 4 different happenings exist simultaneously in 12 dimensions. In principle, we can calculate a wave function representing an infinite number of events happening at the same time in an infinite number of dimensions. No matter how complex the wave function, however, as the state of a system containing n particles is represented at each time by a wave function in a 3-dimensional space. If we make an observation on each of the particles, the wave function is reduced to a special form, to a product of n wave functions, each of which is in a 3-dimensional space. Thus the number of dimensions in the wave function is determined by the number of particles in the system. What happens /77? Soon as we make a measurement, we reduce it to a form compatible with 3-dimensional reality, which is the only form of experimental reality, instant by instant, normally available to us. Now we come to the question, when, exactly, does the wave function collapse? When do all of the possibilities that are developing for the observed system except one, vanish? Up to now, we have said that the collapse occurs when somebody looks at the observed system. This is only one point of view. Another opinion, and discussion about this is opinion, is that the wave function collapses when /look at the observed system. Still another opinion is that the wave function collapses when any measurement is made, even by an instrument. According to this view, it is not important whether we are there to see it or not. Suppose for the moment that there are no human experimenters involved in our experiment. It is entirely automatic. A light source emits a photon. The wave function of the photon contains the possibility that the photon will pass through slit 1 and detector 1 will fire, and also the possibility that the photon will pass through slit 2 and detector 2 will fire. Now suppose that detector 2 registers a photon. According to classical physics, the light source emitted a real particle, a photon. and it traveled from the light source to the slit where detector 2 recorded it. Although we did not know its location while it was in transit, we could have determined it, if we had known how. According to quantum mechanics, this is not so. No real particle called a photon traveled between the light source and the screen. There was no photon until 1 actualized at slit 2. Until then, there was only a wave function. In other words, until then, all that existed were tendencies for a photon to actualize either at slit 1 or at slit 2. From the classical point of view, a real photon travels between the light source and the screen. The odds are 50-50 that it will go to slit 1 and 50-50 that it will go to slit 2. From the point of view of quantum mechanics, there is no photon until a detector fires. There is only a developing potentiality in which a photon goes to slit 1 and to slit 2. This is Heisenberg's strange kind of physical reality just in the mid-DLE between possibility and reality 5. It is difficult to make this sound less vague. The translation 78/patterns of organic energy from mathematics to English entails a loss of precision, but that is not the problem. We can experience a more clearly defined picture of this phenomenon by learning enough mathematics to follow the development of the Schrödinger wave equation. Unfortunately, clarifying the picture only helps to boggle the mind. The real problem is that we are used to looking at the world simply. We are accustomed to believing that something is there or it is not there. Whether we look at it or not, it is either there or it is not there. Our experience tells us that the physical world is solid, real, and independent of us. Quantum mechanics says, simply, that this is not so. Suppose that a technician, not knowing that our experiment is automatic, enters the room to see which detector has recorded a photon. When he looks at the observing system, the detectors, there are 2 things that he can see. The first possibility is that detector 1 has recorded the photon, and the second possibility is that detector 2 has recorded the photon. The wave function of the observing system, which now is the technician, therefore, has 2 humps in it, one for each possibility. Until the technician looks at the detectors, quantum mechanically speaking, both situations in some way exist. As soon as he sees that detector 2 has fired, however, the possibility that detector 1 has fired vanishes. That part of the wave function of the measuring system collapses, and the reality of the technician is that detector 2 has recorded a photon. In other words, the observing system of the experiment, the detectors, has become the observed system in relation to the technician. Now suppose that the supervising physicist enters the room to check on the technician. He wants to see what the technician has learned about the detectors. In this regard, there are 2 possibilities. One is that the technician has seen that detector 1 has recorded a photon, and the other is that the technician has seen that detector 2 has recorded a photon, and so on. The division of the wave function into 2 humps, each one to se the conciseness of mathematical equation. Consider that the entire process described in the theory of measurement from photon system S to detectors, measuring device M, to technician, observer/G, can be represented mathematically by one sentence. What happens /79? Representing a possibility, has progressed from photon to detectors to technician to supervisor. This proliferation of Possibilities is the type of development governed by the Schrödinger wave equation. Without perception, the universe continues, via the Schrödinger equation, to generate an endless profusion of possibilities. The effect of perception, however, is immediate and dramatic. All of the wave function representing the observed system collapses, except one part, which actualizes into reality. No one knows what causes a particular possibility to actualize and the rest to vanish. The only law governing this phenomenon is statistical. In other words, it is up to chance. The division into two parts of the wave function of the photon, detectors, technician, supervisor, etc., is known as the problem of measurement, or, sometimes, the theory of measurement. If there were 25 possibilities in the wave function of the photon, the wave function of the measuring system, technician, and supervisor similarly would have 25 separate humps, until a perception is made, and the wave function collapses from photon to detectors to technician to supervisor. We could continue until we include the entire universe. Who is looking at the universe? Put an other way, how the universe being actualized? The answer comes full circle. We are actualizing the universe. Since we are part of the universe, that makes the universe and us self-actualizing. This line of thought is similar to some aspects of Buddhist psychology. In addition, it could become one of many important contributions of physics to future models of consciousness. The Copenhagen interpretation of quantum mechanics says that it is unnecessary to peer behind the scenes to see what is really happening as long as quantum mechanics works. Correlates experience correctly, in all possible experimental situations. It is not necessary to know how light can manifest itself both as particles and waves. It is enough to know that it does, and to be able to use this phenomenon to predict probabilities. In other words, the wave and particle characteristics of light are unified by quantum mechanics, but at a price. There is no description of reality. The theory of measurement presented here is essentially from John von Neumann's 1932 discussion 80/patterns of organic energy. All attempts to describe reality are relegated to the realm of metaphysical speculation. However, this does not mean that physicists do not speculate. Many do, in particular Henry Stapp, and their reasoning goes like this. The fundamental theoretical quantity in quantum mechanics is the wave function. The wave function is a dynamic, it changes as time progresses, description of possible occurrences. But what does the wave function describe, really? According to Western thought, the world has only two essential aspects, one of which is matter-like and the other of which is idea-like. The matter-like aspect is associated with the external world, most of which is conceived to be made of inanimate stuff that is hard and unresponsive, like rocks, pavement, metal, etc. The idea-like aspect is our subjective experience. Reconciling these two has been a central theme of religion through history. The philosophies which champion these aspects are realism, the world is matter-like, regardless of our impressions. And idealism, reality is idea-like, regardless of appearances. The question is, which one of these aspects does the wave function represent? The answer, according to the orthodox view of quantum mechanics elucidated by Stapp, is that the wave function represents something that partakes of both idea-like and matter-like characteristics. For example, when the observed system as represented by the wave function propagates in isolation between the region of preparation and the region of measurement, it develops. The wave function is the physicist's description of utility at issue is the interpretation of the wave function and whether it is the best possible description, or simple, the only one that fits the language used by the physicists. The wave function, since it is a tool for 0111 understanding of nature, is something. Our thoughts it represents certain specifications of certain physical systems. Specifications are objective in the sense that scientists and technicians can agree on them. However, specifications do not exist apart from thought also. Any given physical system satisfies many sets of specifications, and many physical systems can satisfy one set of specifications. All of these characteristics are idea-like and, to that extent, that which is represented by the wave function is idea-like, even though it is objective. However, these specifications are transcribed into wave functions that develop according to a determined law, the Stjernberg wave equation. This is a matter-like aspect. The thing that develops describes on of probabilities. Probabilities can be thought to describe either things that exist apart from thought, or things that exist only within thought, thus that which the wave function represents are and both idea-like and matter-like characteristics. What happens /81? According to a strictly deterministic law, the Schrödinger wave equation, temporal development in accordance with a causal law is a matter-like characteristic. Therefore, whatever the wave function represents, that something has a matter-like aspect. However, when the observed system as represented by the wave function interacts with the observing system, when we make a measurement, it abruptly leaps to a new state. These quantum leap type transitions are idea-like characteristics. Ideas, like our knowledge about something, can and do change discontinuously. Therefore, whatever the wave function represents, that something also has an idea-like aspect. The wave function, strictly speaking, represents an observed system in a quantum mechanical experiment. In more general terms, it describes physical reality at the most fundamental level, the subatomic, that physicists have been able to probe. In fact, according to quantum mechanics, the wave function is a complete description of physical reality at that level. Most physicists believe that a description of the substructure underlying experience more complete than the wave function is not possible. Wait a minute, says Jim DeWitt, where did he come from? The description contained in the wave function consists of coordinates, 3, 6, 9, etc., and a time, page 75. How can that be a complete description of reality? Imag. In how I felt when my girlfriend ran off to Mexico with a gypsy. Where does that show up in a wave function? It doesn't. The complete description that quantum theory claims the wave function to be is a description of physical reality, as in physics. No matter what we are feeling, or thinking about, or looking at, the wave function describes as completely as possible where and when we are doing it. Since the wave function is thought to be a complete description of physical reality, and since that which the wave Function describes is idea-like as well as matter-like, then physical reality must be both idea-like and matter-like. In other words, the world cannot be as it appears. Incredible as it sounds, this is the conclusion of the orthodox view of quantum mechanics. The physical world appears to be completely substantive, made of stuff. Nonetheless, if it has an idea-like aspect, the physical world is not substantive in the usual sense of the word, 100% matter, 0% idea. According to STAP 82/Patterns of Organic Energy. If the attitude of quantum mechanics is correct, in the strong sense that a description of the substructure underlying experience more complete than the one it provides is not possible, then there is no substantive physical world. In the usual sense of this term, the conclusion here is not the weak conclusion that there may not be a substantive physical world, but rather that there definitely is not a substantive physical world. 6. This does not mean that the world is completely idea-like. The Copenhagen interpretation of quantum mechanics does not go so far as to say what reality is really like behind the scenes, but it does say that it is not like it appears. It says that what we perceive to be physical reality is actually our cognitive construction of it. This cognitive construction may appear to be substantive, but the Copenhagen interpretation of quantum mechanics leads directly to the conclusion that the physical world itself is not. This claim at first appears so preposterous and remote from experience that our inclination is to discard it as the foolish product of cloistered intellectuals. However, there are several good reasons why we should not be so hasty. The first reason is that quantum mechanics is a logically consistent system. It is self-consistent, and it also is consistent with all known experiments. Second, the experimental evidence itself is incompatible with our ordinary ideas about reality. Third, physicists are not the only people who view the world this way. They are only the newest members of a sizable group. Most Hindus and Buddhists also hold similar views. Therefore, it is evident that even physicists who disclaim metaphysics have difficulty avoiding it. Now we come to those physicists who have jumped feet first into describing reality. So far our discussions have been based on the Copenhagen interpretation of quantum mechanics. The unavoidable flaw in this interpretation is the problem of measurement. Some type of detection by an observing system is required to collapse the wave function of the observed system into a physical reality, otherwise the observed system does not physically exist except as an endlessly proliferating number of possibilities generated in accordance with the Schrödinger wave equation. What happens /83? The theory proposed by Hugh Everett, John Wheeler, and Neil Graham solves this problem in the simplest way possible. 7. It claims that the wave function is a real thing, all of the possibilities that it represents are real, and they all happen. The orthodox interpretation of quantum mechanics is that only one of the possibilities contained in the wave function of an observed system actualizes, and the rest vanish. The Everett Wheeler Graham theory says that they all actualize, but in different worlds that coexist with ours. Let's go back to the double-slit experiment again. A light source emits a photon. The photon can pass through slit 1 or through slit 2. A detector is placed at slit 1 and at a slit 2. Now we add a new experimental procedure. If the photon goes through slit 1, I run upstairs if the photon goes through slit 2, I run downstairs. Therefore, one possible occurrence is that the photon goes through slit 1, detector 1 fires. And I run up the stairs. The second possible occurrence is that the photon goes through slit 2, detector 2 fires, and I run down the stairs. According to the Copenhagen interpretation, these two possibilities are mutually exclusive because it is not possible for me to run upstairs and to run downstairs at the same time. According to the Everett-Wheeler-Graham theory, at the moment the wave function collapses, the universe splits into two worlds. In one of them I run up the stairs and in the other I run down the stairs. There are two distinct editions of me. Each one of them is doing something different, and each one of them is unaware of the other, nor will our paths one ever cross, since the two worlds into which the original one split are forever separate branches of reality. In other words, according to the Copenhagen interpretation of quantum mechanics, the development of the Schrödinger wave equation generates an endlessly proliferating number of possibilities. According to the Everett-Wheeler-Graham theory, the development of the Schrödinger wave equation generates an endlessly proliferating number of different branches of reality. This theory is called, appropriately, the many worlds interpretation of quantum mechanics. The theoretical advantage of the many worlds interpretation is that it does not require an external observer to collapse one of the possibilities contained in a wave function into physical reality. According to the many worlds theory 84/patterns of organic energy, wave functions do not collapse, they just keep splitting as they develop according to the Schrödinger wave equation. When a consciousness happens to be present at such a split, it splits also, one part of it associating with one branch of reality, and the other part, S, of it associating with the other branch, S, of reality. However, each branch of reality is exponentially accessible to the other, S, and a consciousness in one branch will consider that branch to be the entirety of reality. Therefore, the role of consciousness, which was central to the Copenhagen interpretation, if consciousness is associated with an act of measurement, is incidental to the many worlds theory. However, the many worlds description of the structure of the relationship between the various branches of physical reality sounds like a quantitative version of a mystical vision of unity. Every state of a subsystem of a composite system is uniquely correlated to the states of the remaining subsystems which constitute the whole of which it is a part. A composite system, in this case, means a combination of both the observed system and the observing system. In other words, every state of the observed system is correlated to a particular state of the observing system. Said another way, the many worlds theory defines any particular branch of reality which might actualize to us as a result of an interaction of an observed system and an observing system as merely one way of decomposing the wave function, which represents them both. According to this theory, all of the other states which could have resulted from the same interaction did happen. But in other branches of reality, each of these branches of reality are real, and, together, they constitute all the different ways in which we can decompose the universal wave function. In this way, the problem of measurement is no longer a problem. The problem of measurement, ultimately, was, who is looking at the universe? The many worlds theory says that It is not necessary to collapse a wave function to actu or /either universe all of the mutually exclusive possibilities contained within the wave function of an observed system that, according to the Copenhagen interpretation, do not actualize when the wave function collapses actually do actualize, but not in this branch of the universe in our experiment. For example, one of the possibilities contained in the wave function actualizes. What happens /85? In this branch of the universe, I run up the stairs. The other possibility contained in the wave function, I run down the stairs, also actualizes, but in a different branch of reality. In this branch of reality I run up the stairs. In another branch of reality I run down the stairs. Neither I knows the other. Both ts behave that their branch of the universe is the entirety of reality. The many worlds theory says that there is one universe, and that its wave function represents all of the waves that it can be decomposed into different possible realities. We are all together here in a big box, and it is not necessary to look at the box from the outside to actualize it. In this regard, the many worlds theory is especially interesting because Einstein's general theory of relativity shows that our universe might be something like a large closed box. And, if this is so, it is never possible to get outside of it. Schrödinger's cat sums up the differences between classical physics, the Copenhagen interpretation of quantum mechanics, and the many worlds interpretation of quantum mechanics. Schrödinger's cat is a dilemma posed long ago. BV, the famous discoverer of the Schrödinger wave equation. A cat is placed inside a box. Inside the box is a device which can release a gas, instantly killing the cat. A random event, the radioactive decay of an atom, determines whether the gas is released or not. There is no way of knowing, outside of looking into the box, what happens inside it. The box is sealed and the experiment is activated a moment later. The gas either has been released or has not been released. The question is, without looking, what has happened inside the box. This is reminiscent of Einstein's unopenable watch. According to classical physics, the cat is either dead or it is not dead. All that we have to do is to open the box and see, which is the case according to quantum mechanics. The situation is not so simple. The Copenhagen interpretation of quantum mechanics says that the cat is in a kind of limbo represented by a wave function which contains the possibility that the cat is dead. And how is one to apply the conventional formulation of quantum mechanics to the space-tune geometry of itself? The issue becomes especially acute in the case of a closed universe. There is no place to stand outside the system to observe it. Hugh Everett High, RU/S of Modern Physics 29 3 1957 455. 86/Patterns of Organic Energy. Also the possibility that the cat is RVT when we look in the box, and not before one of these possibilities actualizes and the other vanishes. This is known as the collapse of the wave function, because the hump in the wave function representing the possibility that did not occur collapses. It is necessary to look into the box before either possibility can occur. Until then, there is only a wave function. Of course, this does not make sense. Experience tells us that a cat is what we put into the box, and a cat is still what is inside the box, not a wave function. The only question is whether the cat is a live cat or a dead cat, but a cat there. Whether we look at it or not, if we take a vacation before we Look inside the box, it makes no difference as far as the cat is concerned. Its fate was decided at the beginning of the experiment. This common-sense view is also the view of classical physics. According to classical physics, we get to know something by observing it. According to quantum mechanics, it isn't there until we do observe it. Therefore, the fate of the cat is not determined until we look inside the box. The man world's interpretation of quantum mechanics and the Copenhagen interpretation of quantum mechanics agree that the fate of the cat is not determined for us until we look inside the box. What happens after we look inside the box, however, depends upon which interpretation we choose to follow. According to the Copenhagen interpretation, at the instant that we look inside the box, one of the possibilities contained in the wave function representing the cat actualizes, and the other possibility vanishes. The cat is either dead or alive. According to the many worlds interpretation, at the instant that the atom decays, or doesn't decay, depending upon which branch of reality we are talking about, the world splits into two branches, each with a different edition of the cat. The wave function representing the cat does not collapse. The cat is both dead and alive at the instant that we look into the box. Our wave function also splits into two branches, one associated with the branch of reality in which the cat is dead, and one associated with the branch of reality in which the T. In practice, it is not deal that a moioscopic ECT such as a catchall K can be represented by a wave function due to the dominating influence of thermodynamicality in irreversible processes. Even so, Schrödinger's cat long has illustrated to physics students the PS/critic aspects of quantum mechanics. What happens /87? Cat is alive, neither consciousness is aware of the other. In short, classical physics says that there is one world, it is as it appears, and this is it. Quantum physics allows us to entertain the possibility that this is not so. The Copenhagen interpretation of quantum mechanics eschews a description of what the world is really like, but concludes that whatever it is like, it is not substantive in the usual sense. The many worlds interpretation of quantum mechanics saves that differ editions of us live in many worlds simultaneously, an uncountable number of them, and all of them are real. There are even more interpretations of quantum mechanics, but all of them are weird in some way. Quantum physics is stranger than science fiction. Quantum mechanics is a theory and a procedure dealing with subatomic phenomena. Subatomic phenomena, in general, are inaccessible to all but those with access to elaborate and expensive facilities. Even at the most expensive and elaborate facilities, however, we can see only the effects of subatomic phenomena. The subatomic realm is beyond the limits of sense or perception. It is also beyond the limits of rational understanding. Of course, we have rational theories about it, but rational has been stretched to include what formerly was nonsense or, at best, paradox. The world that we live in, the world of freeways, bathtubs, and other people, seems as remote as it can be from wave functions and interference. In short, the metaphysics of quantum mechanics is based upon an unsubstantiated leap from the microscopic to the macroscopic. Can we apply these implications of subatomic research to the world at large? No, not if we have to provide a mathematical proof in each instance. But what is a proof? A proof of proves that we are playing by the rules, we make the rules, anvwe, the rules. In this case, are that what we propose about the nature of physical reality, 1. Be logical, consistent, and 2. That it correspond to experience. There is nothing in the rules that saves that what we propose has to be anything like reality. Phys. ICS is a self-consistent explanation of experience. It is in order to satisfy the self-consistency requirement of physics that proofs become important. Asterisk the dark adapted eye can detect single photons ale of the other subatomic particles must be detected indirectly. 88 patterns of organic energy. The New Testament presents a different point of view. Christ, following his resurrection, proved to Thomas, who became the proverbial doubting Thomas, that he really was he, risen from the dead, by showing Thomas his wounds. At the same time, however, Christ bestowed his special favor on those who believed him without proof. Acceptance without proof is the fundamental characteristic of Western religion. Rejection without proof is the fundamental characteristic of Western science. In other words, religion has become a matter of the heart and science has become a matter of the mind. This regrettable state of affairs does not reflect the fact that, physiologically, one cannot exist without the other. Everybody needs both. Mind and heart are only different aspects of us. Who, then, is right? Should disciples believe without proof? Should scientists insist on it? Is the world without substance? Is it real, but divided and dividing into countless branches? The Woolly Masters know that science and religion are only dances, and that those who follow them are dancers. The dancers may claim to follow truth or claim to seek reality. But the Woolly Masters know better. They know that the true love of all dancers is dancing. Part 1. My Way. Chapter 1. The role of tea. In the days before Copernicus discovered that the Earth revolves around the Sun, the common belief was that the Sun, along with the rest of the universe, revolved around the Earth. The Earth was the fixed center of everything. At a still earlier time, in India, this geocentric position was given to people. That is, each person, psychologically speaking, was recognized as being the center of the universe. Although this sounds like an egotistical point of view, it was not, since every person was recognized as a divine manifestation. A beautiful Hindu painting shows Lord Krishna dancing in the moonlight on the bank of the Yamuna. He moves in the center of a circle of fair Vraja women. They are all in love with Krishna and they are dancing with him. Krishna is dancing with all of the souls of the world, man is dancing with himself. To dance with God, the creator of all things, is to dance with ourselves. This is a recurrent theme of Eastern literature. This is also the direction toward which the new physics, quantum mechanics and relativity, seems to point. From the revolutionary concepts of relativity and the logic-defying paradoxes of quantum mechanics, an ancient paradigm is emerging. In vague form, we begin to glimpse a conceptual framework in which each of us shares a paternity in the creation of physical reality. Our old self-image as impotent bystander, one who sees but does not affect, is dissolving. We are watching perhaps the most engaging act in our History. Amid the powerful purr of particle accelerators, the 91, 92 / my way click of computer printouts, and dancing instrument gauges. The old science that has given us so much, including our sense of helplessness before the faceless forces of bigness, is undermining its own foundations. With the awesome authority that we have given it, science is telling us that our faith has been misplaced. It appears that we have attempted the impossible, to disown our part in the universe. We have tried to do this by relinquishing our authority to the scientists. To the scientists we gave the responsibility of probing the mysteries of creation, change, and death. To us we gave the everyday routine of mindless living. The scientists readily assumed their task. We readily assumed ours, which was to play a role of impotence before the ever increasing complexity of modern science and the ever spreading specialization of modern technology. Now, after 3 centuries, the scientists have returned. With their discoveries they are as perplexed as we are, those of them who have given thought to what is happening. We are not sure, they tell us, but we have accumulated evidence which indicates that the key to understanding the universe is you. This is not only different from the way that we have looked at the world for 300 years, it is opposite. The distinction between the in here and the out there upon which science was founded, is becoming blurred. This is a puzzling state of affairs. Scientists, using the in here, out their distinction, have discovered that the in here, out their distinction may not exist. What is out there apparently depends, in a rigorous mathematical sense as well as a philosophical one, upon what we decide in here. The new physics tells us that an observer cannot observe without altering what he sees. Observer and observed are interrelated in a real and fundamental sense. The exact nature of this interrelation is not clear, but there is a growing body of evidence that the distinction between the in here and the out there is illusion. The conceptual framework of quantum mechanics, supported by massive volumes of experimental data, forces contemporary physicists to express themselves in a manner that sounds, even to the uninitiated, like the language of mystics. Access to the physical world is through experience. The common denominator of all experiences is the I that does the role of I/93. The experiencing, in short, what we experience is not external reality, but our interaction with it. This is a fundamental assumption of complementarity. Complementarity is the concept developed by Niels Bohr to explain the wave-particle duality of light. No one has thought of a better one yet. Wave-like characteristics and particle-like characteristics, the theon goes, are mutually exclusive, or complementary aspects of light. Although one of them always excludes the other, both of them are necessary to understand light. One of them always excludes the other because light, or anything else, cannot be both wave-like and particle-like at the same time. How can mutually exclusive wave-like and particle-like be? Have as both be properties of one and the same light? They are not properties of light. They are properties of our interaction with light depending upon our choice of experiment. We can cause light to manifest either particle-like properties or wave-like properties if we choose to demonstrate the wave-like characteristics of light. We can perform the double-slit experiment which produces interference if we choose to demonstrate the particle-like characteristics of light. We can Form an experiment which illustrates the photoelectric effect. We can cause light to manifest both wave-like properties and particle-like properties by performing Arthur Compton's famous experiment. In 1923, Compton played the world's first game of billiards with subatomic particles, and, in the process, confirmed Einstein's 17-year-old photon theory of light. His experiment was not conceptually difficult. He simply fired X-rays, which everybody knows are waves, at electrons. To the surprise of most people, the X-rays bounced off the electrons, as if the X-rays, were particles. For example, the X-rays which struck the electrons glancing blows were deflected on slightly from their paths. THEV did not lose much energy in the collision. However, those X-rays which collided more nearly head-on with electrons were deflected sharply. These X-rays lost a considerable amount of their kinetic energy, the energy of motion, in the collision. Individual events, i.e. all waves titled like wave behavior, is detected as a statistical pattern. I seem to affiance, however, in the words of Paul Dirac, another founder of quantum mechanics, even a single subatomic particle interfere with itself. How a single subatomic particle like an electron, for example, can interfere with itself is the basic quantum paradox. 94/My way. Compton scattering, seen as a wave phenomenon. Incident X-rays, scattered X-rays, lower frequency. Compton scattering, seen as a particle phenomenon. Projectile photons, for scattered photons, lower occupancy. Compton could tell just how much energy the deflected X-rays lost by measuring their frequencies before and after the collision. The frequencies of those X-rays involved in near head-on collisions were noticeably lower after the collision than before it. This meant that they had less energy after the collision than they had before the collision. Compton's X-rays were impacting with electrons exactly the way that billiard balls impact with other billiard balls. Compton's discovery was intimately related to quantum theory. Compton could not have revealed the particle-like behavior of X-rays if Planck had not discovered his fundamental rule that higher frequency means higher energy. This rule permitted Compton to prove that the X-rays in his experiment lost energy in a particle-like collision, because their frequencies were lower after the collision than before the collision. The conceptual paradox in Compton's experiment shows how deeply the wave-particle duality is embedded in quantum mechanics. Compton proved that electromagnetic radiations, like X-rays, have particle-like characteristics by measuring their frequencies. Of course, particles don't have frequencies. Only waves have frequencies. The phenomenon which Compton discovered is called Compton scattering, in honor of what happens to the X-rays. In short, we can demonstrate the light is particle-like with the photoelectric effect, that it is wave-like with the double-slit experiment, and that it is both particle-like and wave-like with Compton scattering. Both of these complementary aspects of light, wave and particle, are necessary to understand the nature of light. It is meaningless to ask which one of them alone is the way light really is. Light behaves like waves. The role of 1/95 or like particles depending upon which experiment we perform. The we that does the experimenting is the common link that connects light as particles and light as waves. The wave-like behavior that we observe in the double-slit experiment is not a property of light, it is a property of our interaction with light. Similarly, the particle-like characteristics that we observe in the photoelectric effect are not a property of light. They, too, are a property of our interaction with light. Wave-like behavior and particle-like behavior are properties of interactions. Since particle-like behavior and wave-like behavior are the only properties that we ascribe to light, and since these properties now are recognized to belong, if complementarity is correct, not to light itself, but to our interaction with light, then it appears that light has no properties independent of us. To say that something has no properties is the same as saying that it does not exist. The next step is this logic is inescapable. Without us, light does not exist. Transferring the properties that we usually ascribe to light to our interaction with light deprives light of an independent existence. Without us, or by implication, anything else to interact with, light does not exist. This remarkable conclusion is only half the story. The other half is that, in a similar manner, without light, or, by implication, anything else to interact with, we do not exist, as Bara himself put it. An independent reality in the ordinary physical sense can be ascribed neither to the phenomena nor to the agencies of observation. 1. By agencies of observation he may have been referring to instruments, not people, but philosophically, complementarity leads to the conclusion that the world consists not of things, but of interactions. Properties belong to interactions, not to independently existing things, like light. This is the way that Bara solved the wave-particle duality of light. The philosophical implications of complementarity became even more pronounced with the discovery that the wave-particle duality is a characteristic of everything. When we left off telling the story of quantum mechanics, the tale had progressed as follows. In 1900, Max Planck, 96/my way, studying black body radiation, discovered that energy is absorbed and emitted in chunks, which he called quanta. Until that time, radiated energy like light was thought to be wave-like. This was because Thomas Young, in 1803, showed that light produces interference, the double-slit experiment, and Onov waves can do that. Einstein stimulated B.V. Planck's discovery of quanta used the photoelectric effect to illustrate his theory that not only are the processes of energy absorption and emission quantized, but that energy itself corner M packages of certain sizes. Thus, physicists were confronted with two sets of experiments, repeatable experiences, each of which seemed to disprove the other. This is the famous wave-particle duality, which is fundamental to quantum mechanics. While physicists were trying to explain how waves can be particles, a young French prince, Louis de Broglie, dropped a bomb which demolished what was left of the classical view. Not only are waves particles, he proposed, but particles are also waves. De Broglie's idea, which was contained in his doctoral thesis, was that matter has waves which correspond to it. The idea was more than philosophical speculation, it was also Mathematical speculation using the simple equations of Planck and Einstein, de Broglie formulated a simple equation of his own asterisk. It determines the wavelength of the matter waves that correspond to matter. It says simply that the greater the momentum of a particle, the shorter is the length of its associated wave. This explains why matter waves are not evident in the macroscopic world. De Broglie's equation tells us that the matter waves corresponding to even the smallest object that we can see are so incredibly small compared to the size of the object that their effect is negligible. However, when we get down to something as small as a subatomic particle like an electron, the size of the electron itself is smaller than the length of its associated wave. Under these circumstances, the wave-like behavior of matter should be clearly evident, and matter should behave different than matter as we are used to thinking of it. This is exactly what happens. Planck's equation E equals height, Einstein's equation E equals me2, de Broglie's equation x equals h/mv. The role of I/97. Only 2 years after de Broglie presented this hypothesis, an experimenter named Clinton Davison, working with his assistant, Lester Germer at the Bell Telephone Laboratories, verified it experimentally. Both Davison and de Broglie got Nobel Prizes, and physicists were left to explain not only how waves can be particles, but also how particles can be waves. The famous Davison-Jenner experiment, which was done by accident, showed electrons reflecting off a still surface in a manner that could be explained only if the electrons were waves. But, of course, electrons are particles. Today, electron diffraction, an apparent contradiction in terms, is a common phenomenon when a beam of electrons is sent through tiny openings, like the spaces between the atoms in a metal foil, which are as small or smaller than the wave lengths of the electrons. Isn't this ridiculous? Particles don't have wavelengths. The beam diffracts exactly the way a beam of light diffracts, although, classically speaking, it can't happen. Here is a picture of it. Asterisk as / on hold. This photograph enchant you the beam of electrons. The transmitted beam is coming dir me is being connected the earth in poke of storm gold toil. The rings on the photo 98 / my way. It was disconcerting enough when light, which is made of waves, began to behave like particles, but when electrons, which are particles, began to behave like waves, the plot became unbearably thick. The unfolding of quantum mechanics was, and still is, a drama of high suspense. Werner Heisenberg wrote, "I remember discussions with Bohrer, in 1927, which went through many hours till very late at night and ended almost in despair, and when at the end of the discussion I went alone for a walk in the neighboring park, I repeated to myself again and again the question, can nature possibly be as absurd as it seemed to us in these atomic experiments?" Subsequent experiments were to reveal that not only subatomic particles, but atoms and molecules as well have associated matter waves. The title of Donald Hughes' pioneer book, Neutron Optics, provides eloquent testimony of the merger between waves and particles to which Prince de Broglie's doctoral thesis gave birth theoretically. In fact, everything has a wavelength: baseballs, automobiles, and even people, although their wavelengths are so small that THEV are not noticeable. de Broglie himself was not very helpful in explaining his theory. It predicted what the Davison-Germer experiment proved, that matter, like electrons, has a wave-like aspect. His equation even foretold the wavelength of these waves. Nonetheless, no one knew what these waves actually were. No one does yet. De Broglie called them waves which correspond to matter, but he did not explain what correspond meant. Is it possible for a physicist to predict something, calculate equations which describe it, and still not know what he is talking about? Yes, as Bertrand Russell put it, mathematics may be defined as the subject in which we graph make the places where that dethact dictum beams stmtk the him, which was placed on the opposite side of the gold foil from that electron source. The white spot m, the center of the photograph, was caused bv nefty acted electrons in the transmitted beam passing through that gold foil and striking the film directly. The roll of I/99. Never know what we are talking about, nor whether what we are saving is true. 3. This is why the physicists at Copenhagen decided to accept quantum mechanics as a complete theory, even though it gives no explanation of what the world is really like, and even though it predicts probabilities and not actual events. They accepted quantum mechanics as a complete theory because quantum mechanics correctly correlates experience. Quantum mechanics, and, according to the pragmatists, all science, is the study of correlations between experiences. De Broglie's equation correctly correlates exponences. De Broglie merged the wave-particle paradox, which came to light, through the genius of Thomas Young, double-slit experiment, and Albert Einstein, photon theory. In other words, he connected the T/O most revolutionary phenomena of physics, the quantum nature of energy and the wave-particle duality. De Broglie presented his matter-wave theory in 1924. During the next 3 years, quantum mechanics crystallized into what it essentially is today, the world of Newtonian physics. Simple mental pictures and common sense disappeared. A new PHYS ICS took form with an originality and force that left the mind reeling. After de Broglie's matter waves came the Schrödinger wave equation. De Broglie's matter wave seemed to Schrödinger, the Viennese physicist, a much more natural way of looking at atomic phenomena than Bohr's planetary model or the atom. Bohr's model of hard, spherical electrons revolving around a nucleus at specific levels and emitting photons by jumping from one level to another explained the color spectrum of simple atoms, but it said nothing about why each shell contains of a certain number of electrons, no more and no less. It also did not explain how the electrons do their jumping, for example, what is happening to them between shells, stimulated BV. De Broglie's discovery, Schrödinger hypothesized that electrons are not spherical objects, but patterns of standing waves. Strictly speaking, Schrödinger's theory does not explain the jump either. In fact, Schrödinger did not like the idea of a jump 100 / my way. Standing waves are familiar phenomena to anyone who has played with a clothesline. Suppose that we tie one end of a rope to a pole, and then pull it tight on this rope. There are no waves at all, either standing or traveling. Now suppose that we flick our wrist sharply downward and then upward. A hump appears in the rope and travels down the rope to the pole where it turns upside down and returns to our hand. This traveling hump, figure, is a traveling wave BV sending a series of humps down the rope. We can set up the patterns of standing waves shown below, and more that are not shown. The simplest of these is the pattern shown in figure B. This pattern is formed BV, the superposition of two traveling waves, a direct one and a reflected one traveling in the opposite direction. It is the pattern, not the rope, which does not move. The widest point in the standing wave remains stationary, and so do the points at the ends of the standing wave. These points are called nodes. There are two of them in the simplest standing pattern, one at our hand and one at the pole where the rope is attached. These stationary patterns, superpositions of traveling waves, are called standing waves. No matter how long or short our rope is, there can be only a whole number of standing waves on it. That is, it can have a pattern of one standing wave, or a pattern of two standing waves, or a pattern of 3, 4, 5, and so on, standing waves, but it can never have a pattern of 1 1/2 standing waves, or a pattern of 2 1/4 standing waves. The standing waves must divide the rope evenly into whole sections. Another way to say this is that we can increase or decrease the number of standing waves on a rope only by a whole number of them. This means that the only way that the number of standing waves on a rope can increase or decrease is discontinuously. That word, again. Furthermore, standing waves on a rope cannot be just ANV size. They always will be restricted to those lengths which divide the rope evenly. The actual size of the waves depends upon how long the rope is, but no matter what length the rope, there will be only certain lengths which divide it evenly. All of this was old stuff. In 1925, plucking a guitar string establishes patterns of standing waves on it. Blowing air into an organ pipe creates standing wave patterns in it. What was new was Schrödinger's realization that standing waves are quantized the same way that atomic phenomena are in the roll-off 1/101 fact. Schrödinger proposed that electrons are standing waves. In retrospect, this is not as fantastic as it first sounds at the time. However, it was a stroke of genius. Picture an electron in orbit around a nucleus. Each time the electron completes a journey around the nucleus, it travels a certain distance. That distance is a certain length, like our rope was a certain length. Similarly, only a whole number of standing waves, never a fraction of one, can form in this length of what is an unanswered question. Schrödinger proposed that each of these standing waves is an electron. In other words, he proposed that electrons are the segments of vibrations bounded by the nodes. So far, we have talked about standing waves on a line, like a clothes line or a guitar string, but standing waves also occur in other mediums, like water. Suppose that we throw a rock into a round pool. Waves radiate from its point of entry. These waves are reflected, sometimes more than once, off different sides of the pool. When the reflected traveling waves interfere with each other, they create a complex pattern of standing waves, which is our old friend, interference. 102/MeWave. Electrons orbit where the crest of one wave meets the trough of another wave. They cancel each other, and the surface of the water along this line of interaction is calm. These calm areas are the nodes which separate the standing waves. In the double slit experiment, the nodes are the dark bands in the pattern of alternating light and dark areas. The light bands are the crests of the standing waves. Schrödinger chose the model of a small tub of water with its complex and intricate interference pattern to explain the nature of the atom. This model is, as he put it, an analog electron waves in an atom-sized basin. The ingenious but nevertheless somewhat artificial assumptions of Baur's model of the atom are replaced by a much more natural assumption in de Broglie's wave phenomena. The wave phenomenon forms the real body of the atom. It replaces the individual punctiform, point-like electrons, which in Baur's model swarm around the nucleus. 4. Standing waves on closest lines have two dimensions, length and width. Standing waves in mediums like water, or on the head of a conga drum, have three dimensions, length, width, and depth. Schrödinger analyzed the standing wave patterns. The role of 3 of the simplest atom, hydrogen, which has only one electron. In hydrogen alone he calculated, using his new wave equation, a multitude of different possible shapes of standing waves. All of the standing waves on a rope are identical. This is not true of the standing waves in an atom. All of them are three-dimensional and all of them are different. Some of them look like concentric circles. Some of them look like butterflies, and others look like mandalas, see below. Shortly before Schrödinger's discovery, another Austrian physicist, Wolfgang Pauli, discovered that no two electrons in an atom can be exactly alike. The presence of an electron with one particular set of properties, quantum numbers, excludes the presence of another electron with exactly the same properties, quantum numbers, within the same atom. For this reason, Pauli's discovery became known as the Pauli. From Modern College Physics, Harvey White, N.Y., Van Nostrand, 1972. These photographs are of mechanical simulations of probability density distributions of different electron states in the hydrogen atom. In other words, they represent where we are most likely to find the point-like electron when we look for it. If the atom is in this or that particular state, there are more states than those shown. Initially, Schrödinger pictured electrons as being tenuous clouds, actually assuming these patterns. A quantum jump can be thought of as a transition from one of these pictures to another without anything in between. 104 My way. Exclusion principle in terms of Schrödinger's standing wave theory. Pauli's exclusion principle means that once a particular wave pattern forms in an atom, it excludes all others of its kind. Schrödinger's equation, modified by Pauli's discovery, shows that there are only two possible wave patterns in the lowest of Baur's energy levels or shells. Therefore, there can be only two electrons in it. There are 8 different standing wave patterns possible in the next energy level, therefore there can be only 8 electrons in it, and so on. These are exactly the numbers of electrons that Baur's model assigns to these energy levels. In this respect, the two models are alike in another important way, however they are different. Baur's theory was entirely empirical, that is, he built it around the experimentally observed facts to explain them. In contrast, Schrödinger built his theory on de Broglie's matter wave hypothesis. Not only does it yield mathematical values, which have been verified experimentally, but it also provides a consistent explanation for them. For example, there are only a certain number of electrons in each energy level, because there are only a certain number of standing wave patterns possible at each energy level. The energy level of an atom jumps only from certain specific values to other certain specific values because standing wave patterns of only certain dimensions can form with the atom and none other. Although Schrödinger was sure that electrons were standing waves, he was not sure what was waving. He was convinced nonetheless that something was waving, and he tailed it pst. A Greek letter pronounced psi, a wave function and a psi function are the same thing. Schrödinger's early interpretation that electrons literally were standing waves did not stand up to detailed examination, and Litt had to renounce it soon. However, the concept of probability based upon a wave function representing an observed system, and developing according to the Schrödinger wave equation, became a fundamental tool in atomic research. Schrödinger's famous equation became an integral part of quantum theory since the Schrödinger wave equation is non-relativistic. However, it does not work at high energies. Therefore, high-energy particle physicists usually use the S matrix to calculate transition probabilities. Dolomat's theory is discussed in a later chapter. The role of I/105. To use the Schrödinger wave equation, we feed it certain characteristics of the atom in question. It then gives us the evolution in time of standing wave patterns which occur in the atom if we prepare an atom in an initial state and let it propagate in isolation. That initial state, while propagating in isolation, evolves in time into different standing wave patterns. The order of these patterns is calculable. The Schrödinger wave equation is the mathematical device which physicists use to calculate the order of these patterns. Said another way, the development of standing wave patterns in an atom is deterministic. Given initial conditions, one pattern always follows another in accordance with the Schrödinger wave equation. The Schrödinger wave equation also provides a self-consistent explanation of the size of the hydrogen atom. According to it, the wave pattern of a system with one electron and one proton, which is what we call a hydrogen atom in its lowest energy state, has an appreciable magnitude only within a sphere which is just the diameter of the smallest Barer orbit. In other words, such a wave pattern turns out to be the same size as the ground state of a hydrogen atom 1. Although Schrödinger's wave mechanics became a pillar of today's quantum mechanics, the useful aspects of Barer's model of subatomic phenomena still are used when the wave theory does not yield appropriate results. In such cases, physicists simply stop thinking in terms of standing waves and start thinking again in terms of particles. No one can say that they are not adaptable in this matter. Wave Schrödinger was convinced that his equations described real things, and not mathematical abstractions. He pictured electrons as actually being spread out over their wave patterns in the form of a tenuous cloud. If the picture is limited to the one electron hydrogen atom, whose standing waves have only 3 dimensions, length, width and depth, this is possible to imagine. However, the standing waves in an atom with 2 electrons exist in 6 mathematical dimensions. The standing waves in an atom with 4 electrons exist in 12 dimensions etc. To visualize this is quite an exercise. At this point, Max Born, a German physicist, put the final until the Paya-Pagatum system interacts with a measuring device that causes an abrupt unpredictable transition to another state, a quantum jump. 106/my way. Touch to the new wave interpretation of subatomic phenomena. According to him, it is not necessary or possible to visualize these waves because they are not real things, they are probability waves. The whole course of events is determined by the laws of probability. To a state in space there corresponds a definite probability, which is given by the de Broglie wave associated with the state. To obtain the probability of a given state we multiply by itself, the amplitude of the matter wave associated with the state. The question of whether de Broglie's equations and Schrödinger's equations represent real things or abstractions was clear to Born. It did not make sense to him to try to think of a real thing that exists in more than 3 dimensions. We have 2 possibilities. Either we use waves in spaces of more than 3 dimensions, or we remain in 3-dimensional space, but give up the simple picture of the wave amplitude as an ordinary physical magnitude, and replace it by a purely abstract mathematical concept, into which we cannot enter. 6. This is exactly what he did. Physics, he wrote, is in the nature of the case indeterminate, and therefore the affair of statistics. 7. This is the same idea, probability waves, that Burr, Kramers, and Slater had thought of earlier. This time, however, using the mathematics of de Broglie and Schrödinger, the numbers came out right. Born's contribution to Schrödinger's theory is what enables quantum mechanics to predict probabilities. Since the probability of a state is found by squaring the amplitude of the matter wave associated with it, and, given initial conditions, the Schrödinger equation predicts the evolution of these wave patterns, the two taken together give a determinable evolution of probabilities. Given any initial state, physicists can predict the probability that an observed system will be observed to be in any other given state at any particular time. Whether or not the observed system is observed to be in that state, how? The role of I/107. Ever, even if that state is the most probable state for that time, is a matter of chance. In other words, the probability of quantum mechanics is the probability of observing an observed system in a given state at a given time if it was prepared in a given initial state. Thus it was that the wave aspect of quantum mechanics developed. Just as waves have particle-like characteristics, Planck, Einstein, particles also have wave-like characteristics. De Broglie. In fact, particles can be understood in terms of standing waves. Schrödinger. Given initial conditions, a precise evolution of standing wave patterns can be calculated via the Schrödinger wave equation. Squaring the amplitude of a matter wave function, gives the probability of the state that corresponds to that wave, Born. Therefore, a sequence of probabilities can be calculated from initial conditions by using the Schrödinger wave equation and Horn's simple formula. We have come a long way from Galileo's experiments with falling bodies. Each step along the path has taken us to a higher level of abstraction, first to the creation of things that no one has ever seen, like electrons, and then to the Abandonment of all attempts even to picture our abstractions. The problem is, however, that human nature being what it is, we do not stop trying to picture these abstractions. We keep asking what are these abstractions of, and then we try to visualize whatever that is. Earlier we dismissed Barr's planetary model of the atom, with the promise that we later would see how physicists currently think of an atom. Well, the time has come, but the task is a thorny one. We gave up our old picture of the atom so easily because we assumed that it would be replaced by one more meaningful, but equally as lucid. Now it develops that our replacement picture is not a picture at all, but an unvisualizable abstraction. This is uncomfortable because it reminds us that atoms were never real things anyway. Atoms are hypothetical entities constructed to make experimental observations intelligible. No one, not one person, has ever seen an atom. Yet we are so used to the idea that an atom is a asterisk if the state is prepared in state asterisk t, the probability that it will be observed to be in state / t is p if it is prepared in state p, t, then the probability that it will be observed in region A at time t is a / 1 x caret x dot t x asterisk xt 108 / miway. Thing that we forget that it is an idea. Now we are told that not only is an atom an idea, it is an idea that we cannot even picture. Nonetheless, when physicists refer to mathematical entities in English, or German or Danish, the words that they use are bound to create images for laymen who hear them, but who are not familiar with the mathematics to which they refer. Therefore, in this lengthy explanation of why it cannot be done, we come now to how physicists today picture an atom. An atom consists of a nucleus and electrons. The nucleus is located at the center of the atom. It occupies only a small part of the atom's volume, but almost all of its mass. This is the same nucleus as in the planetary model. As in the planetary model, electrons move in the general area of the nucleus. In this model, however, the electrons move beyond within an electron cloud. The electron cloud is made of various standing waves which surround the nucleus. These standing waves are not material, they are patterns of potential. The shape of the various standing waves which comprise the electron cloud tells physicists the probability of finding the point electron at any given place in the cloud. In short, physicists still think of an atom as a nucleus around which move electrons, but the picture is not so simple as that of a tiny solar system. The electron cloud is a mathematical concept which physicists have constructed to correlate their experiences. Electron clouds may or may not exist within an atom. No one really knows. However, we do know that the concept of an electron cloud yields the probabilities of finding the electron at various places around the nucleus of an atom, and that these probabilities have been determined empirically to be accurate. In this sense, electron clouds are like wave functions. A wave function also is a mathematical concept which physicists have constructed to correlate their experiences. Wave functions may or may not actually exist. This type of statement assumes a qualitative difference between thought and matter, which may not be a good assumption. However, the concept of a wave function undeniably yields the probabilities of observing a system to be in a given state at a given time if it was prepared in a given way. Like wave functions, electron clouds generally cannot be visualized. An electron cloud containing only one electron, like the electron cloud of a hydrogen atom, exists in 3. The role of I/109 dimensions. All other electron clouds, however, contain more than one electron and therefore exist in more than 3 dimensions. The nucleus of the simple carbon atom, for example, with its 6 electrons, is surrounded by an electron cloud with 18 dimensions. Uranium, with 92 electrons, has an electron cloud of 276 dimensions. Similar, a wave function contains 3 dimensions for each particle that it represents. The situation, in terms of mental pictures, is clearly unclear. This ambiguity results from attempting to depict with limited concepts, language, situations which are not bound by the same limitations. It also masks the fact that we do not know what actually is going on in the invisible subatomic realm. The models that we use are free psychations of the human mind, to use Einstein's words, page 8, that satisfy our innate need to correlate experience rationally. They are guesses about what really goes on inside the unopenable watch. It is extremely misleading to think that they actually describe anything. In fact, a young German physicist, Werner Heisenberg, decided that we never can know what actually goes on in the invisible subatomic realm, and that, therefore, we should abandon all attempts to construct perceptual models of atomic processes. 8. All that we legitimately can work with according to this theory, is what we observe direct of. All we know is what we have at the beginning of an experiment and what we have at the end of it. Any explanation of what actually happens between these two states, which are the observables, page 70, is speculation. Therefore, about the same time, 1925, but independently of de Broglie and Schrödinger, the 25-year-old Heisenberg set about developing a means of organizing experimental data into tabular form. He was fortunate in that 66 years earlier an Irish mathematician named W.R. Hamilton had developed a method of organizing data into arrays, or mathematical tables, called matrices. At that time, Hamilton's matrices were considered the fringe of pure mathematics. Who could have guessed that one dav the backslash would fit like a precut piece into the structure of a revolutionary physics 1. To use Heisenberg's tables, we simply read from them, or calculate from them, what probabilities are associated with what initial conditions. Using this method, which Heisenberg called matrix mechanics, we deal only with physical observer 110 / my way Blaise, which means those things that we know at the beginning of an experiment, and those things that we know about it at the end. We make no speculation about what happens in between. After 25 years of struggling for a theory to replace Newtonian physics, physicists suddenly found themselves with 2 different theories, each one a unique way of approaching the same thing. Schrödinger's wave mechanics, based on de Broglie's matter waves, and Heisenberg's matter mechanics, based on the unavailability of subatomic phenomena. Within a year after Heisenberg developed his matrix mechanics, Schrödinger discovered that it was mathematically equivalent to his own wave mechanics. Since both of these theories were valuable tools for subatomic research, both of them were incorporated into the new branch of physics which became known as quantum mechanics. Much later, Heisenberg applied matrix mathematics to the particle collision experiments of high-energy particle physics. Because such collisions always result in a scattering of particles, it was called the scattering matrix, which was shortened to the S matrix. Today, physicists have two ways to calculate the transition probabilities between what they observe at the beginning of a quantum mechanical experiment and what they observe at the end of it. The first method is the Schrödinger wave equation, and the second method, the S matrix. The Schrödinger wave equation describes a temporal development of possibilities, one of which suddenly actualizes when we make a measurement in the course of a quantum mechanical experiment. The S matrix gives directly the transition probabilities between the observables without giving any indication of a development in time, or the lack of it, or anything else. Both of them work asterisk. As important as was Heisenberg's introduction of matrix mathematics into the new physics, his next discovery shook the very foundations of the exact sciences. He proved that at the subatomic level, there is no such thing as the exact asterisk. The Schrödinger wave equation works at lower energies, however tiny it is non-relativist k. It does not work for high energies, therefore most particle physicists use the S matrix together, perhaps with local relativistic quantum fields, to understand quarks and particles. The role of I/111. Heisenberg's remarkable discovery was that there are limits beyond which we cannot measure accurately. At the same time, the processes of nature, these limits are not imposed by the clumsy nature of our measuring devices or the extremely small SU of the entities that we attempt to measure, but rather by the very wealth that nature presents itself to us. In other words, there exists an ambiguity barred beyond which we never can pass without venturing into the realm of uncertainty. For this reason, Heisenberg's discovery became known as the uncertainty principle. The uncertainty principle reveals that as we penetrate deeper and deeper into the subatomic realm, weight reach a certain point at which one part or another of our picture of nature becomes blurred, and there is no way to reclaim that part without blurring another part of the picture. It is as though we are adjusting a moving picture that is slightly out of focus. As we make the final adjustments, we are astonished to discover that when the right side of the picture clears, the left side of the picture becomes completely unfocused and nothing in it is recognizable. When we try to focus the left side of the picture, the right side starts to blur, and soon the situation is reversed. If we try to strike a balance between these two extremes, both sides of the picture return to a recognizable condition, but in no way can we remove the original foo/mess from them. The right side of the picture, in the original formulation of the uncertainty principle, corresponds to the position in space of a moving particle. The left side of the picture corresponds to its momentum according to the uncertainty principle. %e cannot measure accurately at the same tune both the position and the momentum of a moving particle. The more precisely we determine one of these properties, the less we know \v about the other. If we precisely determine the position of the particle, then, strange as it sounds, there is nothing that we can know about its momentum. If we precisely determine the momentum of the particle, there is no way to determine its position. To illustrate this strange statement, Heisenberg proposed that we imagine a supermicroscope of extraordinarily high resolving power, powerful enough, in fact, to be able to see an electron moving around in its orbit, since electrons are so small we cannot use ordinary light in our microscope because the wavelength of ordinary/light is much too long to see. 112 / my way. Electrons, in the same way that long sea waves barely are influenced by a thin pole sticking out of the water. If we hold a strand of air between a bright light and the wall, the hair casts no distinct shadow, it is so thin compared to the wavelengths of the light that the light waves bend around it instead of being obstructed by it. To see something, we have to obstruct the light waves we are looking within. Other words, to see something, we have to illuminate it with wavelengths smaller than it is. For this reason, Heisenberg substituted gamma rays for visible light in his imaginary microscope. Gamma rays have the shortest wavelength known, which is just what we need for seeing an electron. An electron is large enough, compared to the tiny wavelength of gamma rays, to obstruct some of them to make a shadow on the wall. As it were, this enables us to locate the electron. The only problem, and this is where quantum physics enters the picture, is that, according to Planck's discovery, gamma rays, which have a much shorter wavelength than visible light, also contain much more energy than visible light. When a gamma ray strikes the imaginary electron, it illuminates the electron, but unfortunately, it also knocks it out of its orbit and changes its direction and speed, its momentum, in an unpredictable and uncontrollable way. We cannot calculate precisely the angle of rebound between a particle, like the electron, and a wave, like the gamma ray. In short, if we use light with a wavelength short enough to locate the electron, we cause an undeterminable change in the electron's momentum. The only alternative is to use a less energetic light. Less energetic light, however, causes our original problem, light with an energy low enough not to disturb the momentum of the electron will have a wavelength so long that it will not be able to show us where the electron is. There is no way that we can know simultaneously the position and the momentum of a moving particle. All attempts to observe the electron alter the electron. This is the primary significance of the uncertainty principle. At the subatomic level, we cannot observe something without changing it. There is no such thing as the independent observer who can stand on the sidelines watching nature run its course without influencing it. In one sense, this is not such a surprising statement. The role of I/L3. Good way to make a stranger turn and look at you is to stare intently at his back. All of us know this, but we often discredit what we know when it contradicts what we have been taught is possible. Classical physics is based on the assumption that our reality, independently of us, runs its course in space and time according to strict causal laws. Not only can we observe it, unnoticed, as it unfolds, we can predict its future by applying causal laws to initial conditions. In this sense, Heisenberg's uncertainty principle is a very surprising statement. We cannot apply Newton's laws of motion to an individual particle that does not have an initial location and momentum, which is exactly what the uncertainty principle shows us that we cannot determine. In other words, it is impossible, even in principle, ever to know enough about a particle in the subatomic realm to apply Newton's laws of motion, which, for 3 centuries, were the basis of pH. 6 Newton's laws do not apply to the subatomic realm. Newton's concepts do not even apply in the subatomic realm, given a beam of electrons. Quantum theory can predict the probable distribution of the electrons over a given space at a given time, but quantum theory cannot predict, even in principle, the course of a single electron. The whole idea of a causal universe is undermined by the uncertainty principle. In a related context, Niels Bohr wrote that quantum mechanics, by its essence, entails the necessity of a final renunciation of the classical ideal of causality and a radical revision of our attitude toward the problem of physical reality. 9. Yet there is another startling implication in the uncertainty principle. The concepts of position and momentum are intimately bound up with our idea of a thing called a moving particle. If, as it turns out, we cannot determine the position and momentum of a moving particle, as we always have assumed that we could, then we are forced to admit that this thing that we have been calling a moving particle, whatever it is not the moving particle we thought it was, because strictly speaking, Newton's laws do not disappear totally in the subatomic realm. THEV remain valid as operator equations also in some experiments invoking subatomic particles. Newton's laws may be taken as good approximations in the description of what is happening. 114 / My way. Moving particles always have both position and momentum. As Max Born put it, if we can never actually determine more than one of the two properties, possession of a definite position and of a definite momentum, and if when one is determined, we can make no assertion at all about the other property for the same moment, so far as our experiment goes, then we are not justified in concluding that the thing under examination can actually be described as a particle in the usual sense of the term. 10. Whatever it is that we are observing can have a determinable momentum, and it can have a determinable position, but of these two properties, we must choose, for any given moment, which one we wish to bring into focus. This means, in reference to moving particles anyway, that we can never see them the way they really are, but only the way we choose to see them. As Heisenberg wrote, what we observe is not nature itself, but nature exposed to our method of questioning. The uncertainty principle rigorously brings us to the realization that there is no my way which is separate from the world around us. It brings into question the very existence of an objective reality, as does complementarity and the concept of particles as correlations. The tables have been turned. The exact science is no longer study an objective reality that runs its course regardless of our interest in it or not, leaving us to fare as best we can while it goes its predetermined way. Science, at the level of subatomic events, is no longer exact. The distinction between objective and subjective has vanished, and the portals through which the universe manifests itself are, as we once knew a long time ago, those impotent, passive witnesses to its unfolding, the is, of which we, insignificant we, are examples. The cogs in the machine have become the creators of the universe. If the new physics has led us anywhere, it is back to our selves, which, of course, is the only place that we could go. Part 1. Nonsense. Chapter 1. beginner's mind. The importance of nonsense hardly can be overstated. The more clearly we experience something as nonsense, the more clearly we are experiencing the boundaries of our own self-imposed cognitive structures. Nonsense is that which does not fit into the prearranged patterns which we have imposed on reality. There is no such thing as nonsense, apart from a judgmental intellect which calls it that. True artists and true physicists know that nonsense is only that which, viewed from our present point of view, is unintelligible. Nonsense is nonsense only when we have not yet found that point of view from which it makes sense. In general, physicists do not deal in nonsense. Most of them spend their professional lives thinking along well-established lines of thought. Those scientists who establish the established lines of thought, however, are those who do not care to venture boldly into nonsense, into that which any fool would have told them is clearly not so. This is the mark of the creative mind. In fact, this is the creative process. It is characterized by a steadfast confidence that there exists a point of view from which the nonsense is not nonsense at all, in fact, from which it is obvious. In physics, as elsewhere, those who most have felt the exhilaration of the creative process are those who best have slipped the bonds of the known to venture far into the unexplored territory which lies beyond the barrier of the obvious. This type of person has two characteristics. The first is childlike ability to see the world as it is, and not as it 117. 118 / nonsense appears according to what we know about it. This is the moral of the child's tale, the emperor's new clothes. When the emperor rode naked through the streets, only a child proclaimed him to be without clothes, while the rest of his subjects forced themselves to believe, because they had been told so, that he wore his finest new clothing. The child in us is always naive, innocent in the simplistic sense. A Zen story tells of Nanin, a Japanese master during the Meiji era who received a university professor. The professor came to inquire about Zen. Nanin served tea. He poured his visitor's cup full, and then kept on pouring. The professor watched the overflow until he no longer could restrain himself. It is over full. No more will go in. Like this cup, Nanin said, you are full of your own opinions and speculations. How can I show you Zen unless you first empty your cup? Our cup usually is filled to the brim with the obvious, common sense and the self-evident. Suzuki Roshi, who established the first Zen center in the United States, without trying, of course, which is very Zen, told his students that it is not difficult to attain enlightenment, but it is difficult to keep a beginner's mind. In the beginner's mind, he told them, there are many possibilities, but in the experts there are few. When his students published Suzuki's talks after his death, they called the book, appropriately, Zen Mind, Beginner's Mind. In the introduction, Baker Roshi, the American Zen master, wrote, "The mind of the beginner is empty, free of the habits of the expert, ready to accept, to doubt, and open to all the possibilities." The beginner's mind in science is wonderfully illustrated by the story of Albert Einstein and his theory of relativity. That is the subject of this chapter. The second characteristic of true artists and true scientists is the firm confidence which both of them have in themselves. This confidence is an expression of an inner strength which allows them to speak out, secure in the knowledge that, appearance is to the contrary, it is the world that is confused and not they. The first man to see an illusion by which men have flourished for centuries surely stands in a lonely place. In that beginner's mind /119 moment of insight he, and he alone, sees the obvious which, to the uninitiated, the rest of the world, yet appears as non-sense or, worse, as madness or heresy. This confidence is not the obstinacy of the fool, but the surety of him who knows what he knows, and knows also that he can convey it to others in a meaningful way. The writer, Henry Miller, wrote, "One obey only my own instincts and intuition. I know nothing in advance. Often I put down things which I do not understand myself, secure in the knowledge that later they will become clear and meaningful to me. I have faith in the man who is writing, who is myself, the writer." 2. The songwriter, Bob Dylan, told a press conference, "I just write a song and I know it's going to be all right. I don't even know what it's going to say." An example of this kind of faith in the realm of physics was the theory of light quanta. In 1905, the accepted and proven theory of light was that light was a wave phenomenon. In spite of this, Einstein published his famous paper proposing that light was a particle phenomenon, page 52. Heisenberg described this fascinating situation this way. In 1905, light could either be interpreted as consisting of electromagnetic waves, according to Maxwell's theory, or as consisting of light quanta, energy packets traveling through space with high velocity, according to Einstein. But could it be both? Einstein knew, of course, that the well-known phenomena of diffraction and interference can be explained only on the basis of the wave picture. He was not able to dispute the complete contradiction between this wave picture and the idea of the light quanta. Nor did he even attempt to remove the inconsistency of this interpretation. He simply took the contradiction as something which would probably be understood much later. 4. That is exactly what happened. Einstein's thesis led to the wave-particle duality from which quantum mechanics emerged. And with it, as we know, a way of looking at reality and ourselves that is vastly different from that to which we were accustomed. Although Einstein is known popularly for his 120/nonsense themes of relativity, it was his paper on the quantum nature of light that won him the Nobel Prize. It is also a fine example of confidence in nonsense. What is nonsense and what is not, then, may be merely a matter of perspective. "Wait a minute," interrupts Jim DeWitt, "my uncle Weird George believes that he is a football. Of course, we know that this is nonsense, but Uncle George thinks that we are mad. He is quite certain that he is a football. He talks about it constantly. In other words, he has abundant confidence in his nonsense. Does this make him a great scientist? No, in fact, Weird George has a problem. Not only is he the only person who has this particular perspective, but also this particular perspective is in no way relative to that of any Other observer, which brings us to the heart of Einstein's special theory of relativity. Einstein created two theories of relativity. The first theory is called the special theory of relativity. The second theory, which came later and is more general, is called the general theory of relativity. This chapter and the next are about the first theory, the special theory of relativity. The special theory of relativity is not so much about what is relative as about what is not. It describes in what way the relative aspects of physical reality appear to vary depending upon the point of view of different observers, actually depending upon their state of motion relative to each other, but, in the process, it defines the non-changing absolute aspect of physical reality as well. The special theory of relativity is not a theory that everything is relative. It is a theory that appearances are relative. What may appear to us as a ruler, physicists say rod, 1 foot long, may appear to an observer traveling past us, very fast, as being only 10 inches long. What may appear to us as 1 hour, may appear to an observer traveling past us, very fast, as 2 hours. However, the moving observer can use the special theory of relativity to determine how our ruler and our clock appear to us, if he knows his motion relative to us, and likewise, we can use the special theory of relativity to determine how our stick and our clock appear to the moving observer, if we know our motion relative to him. If we were to perform an experiment at the same moment that the moving observer came past us, both we and the beginner's mind /121 moving observer would see the same experiment, but each of us would record different times and distances, we with our rod and clock and he with his rod and clock. Using the special theory of relativity, however, each of us could transpose our data to the other's frame of reference. The final numbers would come out the same for both of us. In essence, the special theory of relativity is not about what is relative, it is about what is absolute. However, the special theory of relativity does show that appearances are dependent upon the state of motion of the observers. For example, the special theory of relativity tells us that 1. A moving object measures shorter in its direction of motion as its velocity increases until, at the speed of light, it disappears. 2. The mass of a moving object measures more as its velocity increases until at the speed of light it becomes infinite. And 3. Moving clocks run more slowly as their velocity increases until at the speed of light they stop running altogether. All of this is from the point of view of an observer to whom the object is moving, to an observer traveling along with the moving object. The clock keeps perfect time ticking off 60 seconds each minute, and nothing appears to get any shorter or more massive. The special theory of relativity also tells us that space and time are not two separate things, but that together they form space-time, and that energy and mass are actually different forms of the same thing, mass energy. This is not possible, we see RV. It is nonsense to think that increasing the velocity of an object increases its mass, decreases its length and slows its time. Our cup runneth over. These phenomena are not observable in everyday life because the velocities required to make them noticeable are those approaching the speed of light, 186,000 miles per second. At the slow speeds that we encounter in the macroscopic world, these effects are virtually undetectable. If they were, we would discover that a car traveling down the freeway is shorter than it is at rest. weighs more than it does at rest, and that its clock runs slower than it does at rest. In fact, we even would find that a hot iron weighs more than a cold one, because energy has mass and heat is energy. How Einstein discovered all of this is another version of the Emperor's New Clothes. 122/nonsense. Only Albert Einstein looked at two of the major puzzles of his day and saw them with a beginner's mind. The result was the special theory of relativity. The first puzzle of Einstein's time was the constancy of the speed of light. The second puzzle of Einstein's time was the uncertainty, both physical and philosophical, about what it means to be moving or not moving. Wait a minute, we say, what is uncertain about that? 11. If I am sitting in a chair and another person walks past me, then the person walking past me is in motion, and I, sitting in my chair, am not in motion. Quite right, says Jim DeWitt, appearing on cue, but still, it is not that simple. Suppose that the chair in which thou art sitting is on an airplane and that the person walking past you is a stewardess. Suppose also that I am on the ground watching both of you go by. From your point of view, thou art at rest, and the stewardess is in motion, but from my point of view, I am at rest and both of you are in motion. It all depends upon your frame of reference. Your frame of reference is the air plane, but my frame of reference is the earth. DeWitt, as usual, has discovered the problem exactly. Unfortunately, he has not solved it. The earth itself hardly is standing still. Not only is it spinning on its axis like a top, it and the moon are revolving around a common center of gravity, while both of them circle the sun at 18 miles per second. That's not fair, we say. Of course, it is true, but the earth does not seem to be moving to us who live on it. It is only in motion if we change our frame of reference from it to the sun. If we start playing that game, it is impossible to find anything in the entire universe that is standing still. From the point of view of the galaxy, the sun is moving. From the point of view of another galaxy, our galaxy is moving. From the point of view of a third galaxy, the first two galaxies are moving. In fact, from the point of view of each of them, the others are moving. Nicely said, laughs Jim DeWitt, and that is exactly the Einstein's point of departure for the special theory of relativity came from the conflict of classical relativity and Maxwell's prediction of a light speed. Cian often told of tales how Einstein tried to imagine what it would be like to travel as fast as a light wave. He saw, for example, that the hands on a clock would appear to stand still, since no other light waves from the clock would be able to catch up with him until he slowed down. Beginner's Mind /123. Point: there is no such thing as something being absolutely at rest, unequivocally not moving. Motion, and the lack of it, is always relative to something else. Whether we are moving or not depends upon what frame of reference we use. The discussion above is not the special theory of relativity. In fact, the discussion above is a part of the Galilean relativity principle, which is over 300 years old. Any physical theory is a theory of relativity if, like Jim DeWitt, it acknowledges the difficulty of detecting absolute motion or absolute non-motion. A theory of relativity assumes that the only kind of motion that we ever can determine is motion, or lack of it, relative to something else. Galileo's principle of relativity says, in addition, that the laws of mechanics are equally valid in all frames of reference. Physicists save coordinate systems, that move uniformly in relation to each other. The Galilean relativity principle assumes that somewhere in the universe there exists a frame of reference in which the laws of mechanics are completely valid, that is, a frame of reference in which experiment and theory agree perfectly. This frame of reference is called an inertial frame of reference. An inertial frame of reference simply means a frame of reference in which the laws of mechanics are completely valid. All other frames of reference moving uniformly, relative to an inertial frame of reference, are also inertial frames of reference since the laws of mechanics are equally valid in all inertial frames of reference. This means that there is no way that we can distinguish between one inertial frame of reference and an other by performing mechanical experiments in them. Frames of reference moving uniformly, relative to each other, are coordinate systems that move with a constant speed and direction. In other words, they are frames of reference that move with a constant velocity. For example, if, by accident, we drop a book while standing in line at the library, the book falls directly downward in accordance with Newton's law of gravity, and strikes the ground directly beneath the place from which it was dropped. Our frame of reference is the Earth. The Earth is moving at a fantastic speed on its trip around the Sun, but this speed is constant. If we drop the same book while we are traveling on an ideally smooth tram which is moving at a constant speed, the although we do not experience it direct of the orbital motion or the Earth is accelerating. 124 nonsense. Same thing happens. The book falls directly downward in AC accordance with Newton's laws of gravitation and sinks the floor of the train directly beneath the place from which it was dropped. This time, our frame of reference is the train because the train is moving uniformly, with no increases or decreases of speed, in relation to the Earth, and because the Earth is moving in a similar manner in relation to the train. The two frames of reference are moving uniformly relative to each other, and the laws of mechanics are valid in both of them. It does not matter in the least which of the frames of reference is moving. A person in either frame of reference can consider himself moving and the other frame of reference at rest. The Earth is at rest and the train is moving, or the other way round, the tram is at rest and the Earth is moving. From the point of view of physics, there is no difference. What happens if the engineer suddenly accelerates while we are doing our experiment? Then of course, everything is upset. The falling book still will strike the floor of the tram, but at a spot farther back, since the floor of the tram has moved forward beneath the book while it was falling. In this case, the tram is not moving uniformly in relation to the Earth, and the Galilean relativity principle does not apply, provided that all of the motion involved is uniform relative. We can translate motion as perceived in one frame of reference into another frame of reference. For example, suppose that we are standing on the shore watching a ship move past us at 30 miles per hour. The ship is a frame of reference moving uniform relative to us. There is a passenger, a man, standing on the deck of the ship, leaning against the railing. Since he is standing still, his velocity is the same as that of the ship, 30 miles per hour. From his point of view, we are moving past him at 30 miles per hour. Suppose now that the man begins to walk toward the front of the ship at 3 miles per hour. His velocity now, relative to us, is 33 miles per hour. The ship carries him forward at 30 miles per hour and his walking adds 3 miles per hour to that. you get to the top of an escalator. Faster if you walk. Suppose that the man turns around and walks back toward the rear of the ship. His velocity relative to the ship is, again, 3 miles per hour, but his velocity relative to the shore is now 27 miles per hour. In other words, to calculate how fast this passenger moves. Beginner's mind /125. Relative to us, we add his velocity to the velocity of his coordinate system, the ship, if he is walking in the same direction that it is moving, and we subtract his velocity from the velocity of his coordinate system if he is walking in the opposite direction. This calculation is called a classical, Galilean, transformation. Knowing the uniform relative motion of our two frames of reference, we can transform the passenger's velocity in reference to his own coordinate system, 3 miles per hour, into his velocity in reference to our coordinate system, 3 miles per hour. The freeway provides abundant examples of classical transformations from one frame of reference to another. Suppose that we are driving at 75 miles per hour. We see a truck coming toward us. Its speedometer also reads 75 miles per hour. Making a classical transformation, we can say that, relative to us, the truck is approaching at 150 miles per hour. Which explains why head-on collisions so often are fatal. Suppose now that a car going in the same direction that we are going passes us. His speedometer reads 110 miles per hour. It's a Ferrari, again, making a classical transformation. We can say that relative to us, the Ferrari is departing our location at 35 miles per hour. The transformation laws of classical mechanics are common sense. They say that when though we cannot determine whether a frame of reference is absolutely at rest or not, we can translate velocities and positions from one frame of reference into velocities and positions in other frames of reference, provided that the frames of our reference are moving uniformly relative to each other. Furthermore, the Galilean relativity principle, from which Galilean transformations come, says that if the laws of mechanics are valid in any one frame of reference, they also are valid in any other frame of reference, moving uniformly relative to it. Unfortunately, there is one catch in all this. No one yet has found a coordinate system in which the laws of mechanics are valid. What impossible can't be, we cry aghast. What about the Earth? Well, it is true that Galileo, who first probed the laws of classical mechanics, used the Earth as a frame of reference. Although not consciously, the idea of coordinate stems did. That xitars provide such a RTKRTNTT frame is for is defining rotation. 126 nonsense. Not come along until Descartes, however, our present Mes. /ices are more accurate than Galileo's, who occasion ally even used his pulse, which means that the more excited he got, the more inaccurate his measurements became. Whenever we reconstruct Galileo's falling body experiments, we always find discrepancies between the theoretical results that we should get and the experimental results that we actually do get. These discrepancies are due to the rotation of the Earth. The bitter truth is that the laws of mechanics are not valid for a coordinate system rigidly attached to the Earth. The Earth is not an inertial frame of reference. Since their very inception, the poor laws of classical mechanics have been left, so to speak, without a home. No one has discovered a coordinate system in which they manifest themselves perfectly. This leaves us, from a physicist's point of view, in a pretty mess. On the one hand, we have the laws of classical mechanics, which are indispensable to physics, and on the other hand, these same laws are predicated upon a coordinate system, which may not even exist. This problem is related to relativity, which is the problem of determining absolute non-motion, in an intimate way. If such a thing as absolute non-motion were detected, then a coordinate system attached to it would be the long-lost Marshall frame of reference, the coordinate system in which the classical laws of mechanics are perfectly valid. Then everything would make sense again, because, given a frame of reference in which the classical laws of mechanics are valid, any frame of reference the classical laws of mechanics at last would have a permanent mailing address. Physicists do not enjoy theories with loose ends. Before Einstein, the problem of detecting absolute motion, or absolute non-motion, if we find one, we find the other, and the problem of finding an Marshall coordinate system were, to say the least, loose ends. The entire structure of classical mechanics was based on the fact that somewhere, somehow, there must be a frame of reference in which the laws of classical mechanics are valid. The inability of physicists to find it made classical mechanics appear exactly like a huge castle built on sand. Although no one, including Einstein, discovered absolute non-motion, the inability to detect it was a major concern of Einstein's day. The second major controversy of Einstein's beginner's mind /127 day, not counting Planck's discovery of the quantum, was an incomprehensible, logic-defying characteristic of light. In the course of their experiments with the speed of light, physicists discovered something very strange. The speed of light disregards the transformation laws of classical mechanics. Of course, that's impossible, but nevertheless, experiment after experiment proved just the opposite. The speed of light just happens to be the most nonsensical thing ever discovered. That is because it never changes. So light always travels at the same speed. We ask, /Vts. So strange about that? OMV, oh my, says a distraught physicist circa 1887. You simply don't understand the problem. The problem is that no matter what the circumstances of the measurement, no matter what the motion of the observer, the speed of light always measures 186,000 miles per second *. Is this bad? We save, beginning to sense that something is strange here. Worse, says the physicist, it's impossible. Look, he tells us, trying to calm himself, suppose that we are standing still and that somewhere in front of us is a light bulb that also is standing still. The light bulb flashes on and off and we measure the velocity of the light that comes from it. What do you suppose that velocity / will be? 186,000 miles per second, we answer, the speed of light. Correct, saves the physicist, with a knowing look that makes us uncomfortable. Now, suppose the light bulb still is standing still, but we are moving toward it at 100,000 miles per second. Now what will we measure? The speed of the light / 286,000 miles per second. We answer the speed of light 186,000 miles per second, plus our speed, 100 miles per second. This is a typical example of a classical transformation. Wrong one, shouts the physicist. That's just the point. The speed of the light is still 186,000 miles per second. Wait a minute, we save that. Can't be. You save that if the light bulb is at rest and we are at rest, the speed of photons. Asterisk in a vacuum tube bead, all light changes in matter depending upon that index of refraction of the matter. C. Weight TTR equals index of refraction 128 / nonsense. Emitted from it will measure the same to us as the speed of photons emitted from it when we are rushing toward the light bulb. That doesn't make sense. When the photons are emitted, they are traveling at 186,000 miles per second. If we also are moving toward them, their velocity should measure that much faster. In fact, they should appear to be traveling with the speed at which they were emitted plus our speed. Their velocity should measure 186,000 miles per second plus 100,000 miles per second. True, says our friend, but it doesn't. It measures 186,000 miles per second, just as if we still were standing still. Pausing for that to sink in, he continues, now consider the opposite situation. Suppose that the light bulb still is standing still, and this time we are moving away from it at 100,000 miles per second. What will the velocity of the photons measure? You now. 86,000 miles per second. We say, hopefully, the speed of light minus our speed as we move away from the approaching photons. Wrong, again. Exclaims our friend again. It should, but it doesn't. The speed of the photons still measures 186,000 miles per second. This is very hard to believe. Do you mean that if a light bulb is at rest and we measure the speed of the photons emitted from it while we also are at rest, and if we then measure the speed of the photons from it while we are moving toward it, and lastly, if we measure the speed of the photons emitted from it while we are moving away from it, we get the same result in all three cases. Exactly, says the physicist. 186,000 miles per second. Asterisk. Do you have any evidence? We ask him. Unfortunately, he says, I do. Two American physicists, Albert Michelson and Edward Morley, have just completed an experiment which seems to show that the speed of light is constant, regardless of the state of motion of the observer. Asterisk. The reverse situation, the source moves and the observer remains stationary, one, is explainable in terms of pre-relativistic physics. In fact, if light is assumed to be a wave phenomenon governed by a wave equation, it is expected that its measured velocity will be independent of the velocity of its source. The velocity of the sound waves reaching us from a jet plane, for example, does not depend upon the velocity of the aircraft. They propagate through a medium, the atmosphere, at a given velocity, from their point of origin, regardless of the motion of the plane. The frequency of the sound shifts as the source moves. Beginner's Mind /129. This can't happen, he sighs, but it is happening. It just doesn't make sense. The problem of absolute non-motion and the problem of the constancy of the speed of light converged in the Michelson-Morley experiment. The Michelson-Morley experiment, 1887, was a crucial experiment. A crucial experiment is an experiment which determines the life or death of a scientific theory. The theory that was tested by the Michelson-Morley experiment was the theory of the ether. The theory of the ether was that the entire universe lies in and is permeated by an invisible, tasteless, odorless substance that has no properties at all, and exists simply because it has to exist so that light waves can have something to propagate in. For light to travel as waves, according to the theory, something has to be waving. That something was the ether. The theory of the ether was the last attempt to explain the universe by explaining some effort. Interpreting the universe in terms of things, like the great machine idea, was the distinguishing characteristic of the mechanical view, which means all of physics from Newton until the middle 1800s. The ether, according to the theory, is everywhere and in everything. We live and perform our experiments in a sea of ether. To the ether, the hardest substance is as porous as a sponge to water. There are no doors to the ether. Although we move in the ether sea does not move. It is absolutely, unequivocally not moving. Therefore, although the primary reason for the existence of the ether was to give light something to propagate through, its existence also solved the old problem of locating the original inertial coordinate system, that frame of reference in which the laws of mechanics are completely valid. If the ether existed, and it had to exist, the coordinate system attached to it was the coordinate system against which all others could be compared to see if they were moving or not. The findings of Michelson and Morley gave a verdict of, for example, the Doppler effect. Pre-relativity theory assumes a medium, like the atmosphere, for sound WVES, or the ether, for light waves, through which the waves propagate. The paradox is that the measured velocity of light has been found, the Michelson-Morley experiment, to be independent of the motion of the observer. In other words, assuming a light wave propagating through a medium, how can we move through the same medium toward the approaching wave without increasing its measured velocity? 130 nonsense. Death to the theory of the ether * equally important, they led to the mathematical foundations of Einstein's revolutionary new theory. The idea of the Michelson-Morley experiment was to determine the motion of the Earth through the ether sea. The problem was how to do this. Two ships at sea can determine their motion relative to one another, but if only one ship moves through a smooth sea, it has no reference point against which to measure its progress. In the old days, seamen would throw a log overboard, and measure their progress relative to it. Michelson and Morley did the same thing, except that the log that they threw overboard was a beam of light. Their experiment was conceptually simple and ingenious. If the Earth is moving, THEV reasoned, and the ether sea is at rest, then the movement of the Earth through the ether sea must cause an ether breeze. Therefore, a beam of light traveling against the ether breeze should have a slower velocity than a beam of light sent across the ether breeze. This is the essence of the Michelson-Morley experiment. Every pilot knows that it takes longer to fly a given distance if one leg of the trip is against a headwind, even though the return leg is with a tailwind, than it takes to fly the same distance across the same wind. Similarly, thought Michelson and Morley, if the theory of the ether sea is correct, a light beam sent upstream against the ether breeze and then downstream with it will take longer to return to its starting point than a light beam sent back and forth across the either breeze. To establish and detect this difference in velocity, Michelson and Morley created a device called an interferometer. From the word interference, it was designed to detect the interference pattern created by the two beams of light as they returned to a common point. A light source emits a beam of light toward a half-silvered mirror, similar to the lenses in sunglasses that look like a mirror on one side, but are transparent from the other side. The original beam of light, is split by the half-silvered mirror into two segments, each of which travels an equal distance, but at right angles to each. Quantum field theory resurrects a new kind of ether, e.g. particles are excited states or the featureless ground state of the held, the vacuum state. The vacuum state is so featureless and has such high symmetry that we cannot assign a velocity to it experimentally. Beginner's Mind /131. Other, and back again, the two beams then reunite via the same half-silvered mirror and travel, into a measuring device by observing the interference created by these converging beams in the measuring device. Any difference in velocity between them can be determined accurately. When the experiment was performed, not the slightest difference in velocity could be detected between the two beams of light. The interferometer was turned 90 degrees so that the beam going against the ether wind now was directed across it, and the beam going across the ether wind now was sent directly into it. Again, not the slightest difference in velocity between the two beams could be detected. In other words, the Michelson-Morley experiment had failed to prove the existence of the ether unless an explanation could be found. Physicists would be faced with choosing between two unsettling alternatives: either 1. The Earth is not moving, and Copernicus was wrong, or 2. The ether does not exist. Neither of these was very acceptable. Michelson and Morley thought that perhaps the Earth I32 /nonsense read a layer of ether with it as it moved through the ether set, just as it carries its atmosphere with it as it travels through space and, therefore, close to the surface of the Earth, the ether breeze cannot be detected. No one had a better hypothesis until an Irishman named George Francis Fitzgerald proposed, in 1892, an outrageous explanation. Fitzgerald reasoned that perhaps the pressure of the ether wind compresses matter just as an elastic object moving through water becomes shortened in the direction that it is traveling. If this were true, then the arm of the interferometer pointing into the ether wind would be somewhat shorter than the arm that is not pointing into it. Therefore, a reduction in the velocity of the light traveling into the ether wind and back might not be detected because the distance that the light travels also is reduced. In fact, if the amount by which the interferometer arm pointing into the ether wind is shortened just corresponds to the amount by which the velocity of the light traveling up that arm and back is reduced, then both beams of light in the experiment will reach the measuring device at exactly the same time, the beam with the higher velocity traversing a greater distance in the same time that the beam with the slower velocity traverses a lesser distance. Fitzgerald's hypothesis had a major advantage over all the others. It was impossible to disprove it. Said simple that there is a one-dimensional contraction in the direction of motion that increases as velocity increases. The catch is that everything Contracts if we want to measure the length of an object that is moving very fast compared to the speed of light, we have to catch up with it first, and when we do, according to the theory, the measuring stick that we are carrying with us also contracts if the object measured 17 inches at rest. It still would measure 17 inches, nor would anything look contracted, because the lenses in our eyes also would contract, distorting them just enough to make everything look normal. 1 year later, a Dutch physicist, Hendrik Antoon Lorentz, while working on another problem, independently arrived at Fitzgerald's hypothesis. Lorentz, however, expressed his discovery in rigorous mathematical terms. This, of course, upgraded Fitzgerald's hypothesis to a position of respectability, and it began to gain a surprising degree of acceptance. Considering its fantasy-like quality, Lorentz's mathematical for beginner's mind /133 Mulations of the Fitzgerald-Lorentz contraction became known as the Laurent-transformations. The stage was now set, all of the scenery was in place. The failure to detect the ether, the Michelson-Morley experiment *. The constancy of the speed of light, the Fitzgerald-Lorentz contractions, the Laurent-transformations. These are the FARTs that continued to confuse physicists at the beginning of the center, all of them but Albert Einstein. When he looked at these pieces of scenery, what his beginner's mind saw was the special theory of relativity. It is said that the Leisen-McP theory of Eclatuit did not experiment how /ei the itsu the n for 18 years no, and the / led to the Leutenstrae is BV, which Einstein discovered the special Uhidai, the results of the Michelson-Morley LTS of this / vel publicized experiment in to Einstein's papsci on special Lelatmti, 1905. Sformations, which became central to the mathematical Foimisny of Special Relativity. Chapter 1. Special Nonsense. Einstein's first professional act, upon reviewing the facts, was the equivalent of saying, "But the emperor's not wearing any clothes," except what he said was, "The ether does not exist." The first message of the special theory of relativity is that, since the ether is undetectable and, in effect, useless, there is no reason to continue the search for it. It is undetectable because every attempt to measure it or determine its quality, culminating with the /1 Michelson-Morley experiment, failed utterly even to indicate its presence. It is useless because light propagation can be envisioned as the propagation of energy through empty space, in vacuum, according to Maxwell's field equations, as well as it can be envisioned as a disturbance of the ether medium. Einstein stated clearly what already was implicit in Maxwell's equations. Maxwell was the discoverer of the electromagnetic field. The electromagnetic fields, he wrote, are not states of a medium, the ether, and are not bound down to an bearer, but they are independent realities, which are not reducible to anything else. To this assertion was supported BV the inability of physicists to detect the ether. With this statement, Einstein brought to a close the illustrious history of mechanics, the idea that physical events are explicable in terms of things. Classical mechanics is the story of objects and forces between them. It was a remarkable break from a 3-century-old tradition to assert blatantly, in the early 1900s, that electromagnetic fields involve no object whatever, that they are not states of the ether medium, but 134. Special nonsense /135. Ultimate, irreducible realities 3 in themselves henceforth. As in quantum mechanics, there would be no concrete imagery associated with physical /. Both relativity and quantum theory heralded the unprecedented remoteness from experience which has characterized physical theory ever since. In fact, the trend is continuing as, though governed by an inexorable law, physics is becoming more and more abstract as it covers wider and wider tracts of experience. Only the future will tell if this trend is reversible. The second victim of Einstein's inability to see clothes that weren't there was absolute non-motion. Why should we make one particular frame of reference privileged for in respect to all others, BV saving that it alone absolutely is not moving? It may be desirable theoretically, but since such a frame of reference does not constitute a part of our experience, it should be disregarded. It is not able to place in a theoretical structure a characteristic which has no corresponding characteristic in our system of experience. In one stroke, Einstein eliminated the two major physical and philosophical blocks to a radically new way of perceiving it / with no ether and no concept of absolute motion to confuse the situation became much simpler. Einstein's next step was to confront the puzzle which had come to light, no pun, in the Michelson-Morley experiment. Namely, the constancy of the speed of light. How could the speed of light be 186,000 miles per second regardless of the state of motion of the observer? In an ingenious mental turnaround, Einstein turned this puzzle into a postulate. Instead of worrying for the moment about how it can happen, he simply accepted the experimentally irrefutable fact that it does happen. This evident to us recognition of the obvious was the first step in a logical process, which, once set in motion, was to explain not only the puzzle of the constant speed of light, but a great deal more. The puzzle of the constancy of the velocity of light became the principle of the constancy of the velocity of light. The principle of the constancy of the velocity of light is the first foundation stone of the special theory of relativity. The principle of the constancy of the velocity of light is that whenever we make a measurement of the velocity of light, regardless of whether we are in motion or at rest relative to the light source, we always get the same result. The speed of 136 / nonsense light is invariably 186,000 miles per second *. This is what Michelson and Morley discovered in their famous experiment. From the point of view of classical mechanics, the principle of the constancy of the velocity of light makes no sense at all. In fact, it conflicts violently with common sense. Before Einstein, the totalitarian grasp of common sense held the constancy of the speed of light to the status of a paradox. Whenever we bump into the limits of our self-imposed cognitive reality, the result is always paradox. It took a pure beginner's mind, such as Albert Einstein's, to accept that if what is the constancy of the velocity of light, then common sense must be u/wrong. The most important victim of Einstein's beginner's mind was the whole structure of classical, Galilean, transformations. That sweet but illusory fiat of a common sense anchored in macroscopic dimensions and velocities. To give up common sense is not an easy task. Einstein was the first person to do it. in such a wholesale manner that his perception of the very nature of space and time changed radically. Moreover, when all was said and done, Einstein's vision of space and time turned out to be more useful than that of common sense. The second foundation stone of the special theory of relativity is the principle of relativity. When Einstein dismissed the idea of absolute non-motion, his theory became ipso facto a theory of relativity, since there was no better principle of relativity to be had than Galileo's. Einstein's NNPLV borrowed it, but first, of course, he brought it up to date. Galileo's principle of relativity saves that the laws of Macquorn ICS, such as the laws governing falling bodies, that are valid in one frame of reference are valid in all frames of reference that move uniformly, without jerkness, in relation to it. Another way of saying the same thing is that it is impossible to determine, by doing experiments involving the laws of mechanics, whether or not our frame of reference is moving or at rest in relation to another frame of reference in which the laws of mechanics also are valid. Einstein expanded the Galilean relativity principle to include all the laws of physics, and not just the laws of classical mechanics. In particular, he included the laws governing in a /unium the speed of light changes in matter depending upon the index of diffraction of the matter. Special nonsense /137. Electromagnetic radiation, which were unknown in Galileo's time. Einstein's updated principle of relativity, then, is that all the laws of nature are exactly identical in all frames of references that move uniformly relative to each other, and that therefore there is no way of distinguishing absolute uniform motion, or non-motion. In short, the two foundation stones of the special theory of relativity are the principle of the constancy of the velocity of light, the Michelson-Morley experiment, and the principle of relativity. Galileo said more specifically, the special theory of relativity rests upon these two postulates. 1. The velocity of light in a vacuum is the same in all frames of reference, for all observers, moving uniformly, relative to each other, and 2. All laws of nature are the same in all frames of reference, moving uniformly, relative to each other. Of these two postulates, the first one, the principle of the constancy of the velocity of light, is the troublemaker. There is no way that it and the classical transformation laws both can be true according to the classical transformation laws, and common sense. The speed of light must be its velocity as it is emitted from a source plus or minus the velocity of the observer, if the observer is moving toward the source or away from the source. According to experiment, the speed of light remains constant regardless of the state of motion of the observer. Common sense and experimental findings are in violent disagreement. Einstein's beginner's mind told him that, since we cannot argue with what is the experimental evidence, then our common sense must be wrong. With this decision to disregard common sense and to base his new theory on the only clothes he could see that the emperor was wearing, the constant speed of light and the principle of relativity, Einstein stepped boldly into the unknown, in fact, into the unimaginable. Already on new territory, he proceeded to explore where no person had gone before. How could it be that to every observer the speed of light is the same regardless of their state of motion? 1. To measure speed, it is necessary to use a clock and ruler, a rigid rod. If the Speed of light as measured by an observer at rest relative to a light source is the same as the speed of light as measured by an observer in motion relative to the source, then it must be 138 nonsense. That, somehow, the measuring instruments change from one frame of reference to the other in just such a way that the speed of light always appears to be the same. The speed of light appears constant because the rods and clocks used to measure it vary from one frame of reference to another depending upon their motion. In short, to an observer at rest, a moving rod changes its length and a moving clock changes its rhythm at the same time. To an observer traveling along with a moving rod and clock, there is no apparent change at all in length or thm. Therefore, both observers measure the speed of light to be the same, and neither can detect anything unusual in the measurement or in the measuring apparatus. This is very similar to the case of the Michelson-Morley experiment according to Fitt-Gerald and Lawrence. The arm of the interferometer that faces into the ether wind, now dismissed from our theory, is shortened bv the pressure of the ether wind. Therefore, the light that travels the interferometer arm facing into the ether wind has less distance to travel and more time to do it in than does the light traveling the other arm. As a result, the speed of light traveling both arms appears to be the same. This is what the Lorentz transformations do. Scribe, come to think of it, the Lorentz transformations can be used to describe contractions due to motion as well as contractions due to a fictitious ether wind. Fitzgerald and Lawrence imagined that rigid rods were pressed under the pressure of the ether wind, but according to Einstein, it is motion, it's forward slash that causes contraction, and in addition time dilation. Here is another way of looking at it. A constant velocity of light is exactly what would result if moving measuring rods became shorter and moving clocks ran more slowly, because a moving observer would measure the speed of light with a shorter measuring rod, less distance for the light to travel, and a slower clock, more tuned to do it in, than an observer at rest. Each observer, however, would consider his own rod and clock to be quite normal and unimpaired. Therefore, both observers would find the speed of light to be 186,000 miles per second, and both of them would be /led bv. This fact, if they were still bound by the classical transformation laws. These were the initial fruits of Einstein's basic assumptions: the principle of the constancy of the velocity of light and the principle of relativity. First, a moving object appears to special nonsense /139 act in its direction of motion and become shorter as its velocity increases until, at the speed of light, it disappears altogether. Second, a moving clock runs more slowly than a clock at rest, and continues to slow its rhythm as its velocity increases, until, at the speed of light, it stops running altogether. These effects only appear to a stationary observer, one who is at rest relative to the moving clock and rod. They do not appear to an observer who is traveling along with the clock and rod. To make this clear, Einstein introduced the labels proper and relative. What we see when we observe our stationary rod and our stationary clock, if we ourselves are stationary, is their proper length and proper time. Proper means one's own. Proper lengths and proper times always appear normal. What we see if we are stationary and observe a rod and a clock traveling very fast relative to us is the Relative length of the moving rod and the relative time of the moving clock. The relative length is always shorter than the proper length, and the relative time is always slower than the proper time. The time that you see on your own watch is your proper time, and the time that you see on the watch of the person moving past you is the relative time, which appears to you, not to the person moving past you, to run more slowly. The length of the measuring rod in your own hand is its proper length, and the length of the measuring rod in the hand of the person moving past you is its relative length, which appears to you, but not to the other person, to be shorter. From the point of view of the person moving past you, he is at rest, you are moving. And the situation is reversed. Suppose that we are aboard a spacecraft outward bound on an exploration. We have made arrangements to press a button every 15 minutes to send a signal back to Earth. As our speed steadily increases, our Earthbound colleagues notice that instead of every 15 minutes, our signals begin to arrive 17 minutes apart, and then 25 minutes apart. After several days, our colleagues, to their distress, find that our signals arrive every 2 days. As our velocity continues to increase, our signals become years apart. Eventually, generations of Earthonks come and go between our signals. Meanwhile, on the spacecraft, we are entirely unaware of the predicament back on Earth. As far as we are concerned, everything is proceeding according to plan, although we are becoming bored with the routine of pressing a button every 140 / 15 minutes. When we return to Earth, a few years older, our proper time, we may find that we have been gone, AC, according to Earth time, for centuries. The relative time, exactly how long, depends upon how fast we have been going. This scene is not science fiction. It is based upon a well-known, to physicists, phenomenon called the twin paradox of the special theory of relativity. Part of the paradox is that one twin remains on Earth while the other goes on a space voyage and returns, younger than his brother. There are many examples of proper time and relative time. Suppose that we are in a space station observing an astronaut who is traveling at a speed of 161,000 miles per second relative to us. As we watch him, we notice a certain sluggishness in his movements, as though he were moving in slow motion. We also notice that everything in his spaceship also seems to function in slow motion. His rolled cigarette, for example, lasts twice as long as one of ours. Of course, part of his sluggishness is due to the fact that he is fast increasing the distance between us, and with each passing moment, it takes the light from his spaceship longer to reach us. Nonetheless, after making allowances for the travel time of the light involved, we find that the astronaut still is moving more slowly than usual. However, to the astronaut, it is we who are zipping past him at 161,000 miles per second, and after he makes all the necessary allowances, he finds that it is we who are sluggish. Our cigarette lasts twice as long as his. This situation could be the ultimate illustration of how the grass is always greener on the other side. Each man's cigarette lasts twice as long as the others, unfortunately. So does each man's trip to the dentist. The time that we ourselves experience and measure is our proper time. Our cigarette lasts the normal length of time. The time that we measure for the astronaut is the relative time. His cigarette appears to last twice as long as ours. Because his time passes twice as slowly, the situation is similar. Regarding proper lengths and relative lengths from our point of view, the astronaut's cigarette, provided that it is pointing in the direction that his spaceship is moving, is shorter than our own cigarette. The other side of the coin is that the astronaut sees himself as stationary and his cigarettes as normal. He also sees us as traveling at 161,000 miles per second relative to him, and our special nonsense /141 cigarettes as shorter than his and slower burning. Einstein's theory has been substantiated in many ways. All of them verify it with awesome accuracy. The most common verifications of time dilation come from high-energy particle physics. A very light elementary particle, called a muon, pronounced muon, is created at the top of the Earth's atmosphere by the collision of protons, one form of cosmic radiation, and air molecules we know from experiments in which muons are created in accelerators that they live a very short time. By no means do they live long enough to eat the Earth from the upper atmosphere. Long before the time it takes to traverse this distance, they should decay spontaneously into other types of particles, yet this does not happen because we detect them in abundance here at the Earth's surface. Why do the muons created by cosmic radiation live longer? In fact, 7 times longer than those muons created in the laboratory. The answer is that the muons produced by collisions of cosmic radiation and air molecules travel much faster than any muons that we can create experimentally. Their velocity is approximately 99% of the speed of light. At that speed, time dilation is quite noticeable. They do not live longer than usual from their point of view, but from our point of view they live 7 times longer than they would at slower velocities. This is true not only of muons but of almost all subatomic particles, and there are many of them. For example, pions. Pions, another type of subatomic particle which move at 80% of the speed of light, live, on the average 167 times as long as slow pions. The special theory of relativity tells us that the intrinsic lifetime of these high-speed particles does not increase, but that their relative rate of time flow slows down. The special theory of relativity also made the calculation of these phenomena possible long before we had the technical capability to create them. In 1972, 4 of the most accurate atomic clocks available were put aboard an aircraft and flown around the world. At the end of the trip, they were found to be slightly behind their stationary, earthbound counterparts with which they were synchronized before the flight. The next time that you fly. The clocks were flown around the world each way, east and west, both general relativistic and special relativistic effects were noted. J.C. Hilt Ind. R.E. Chemische Science Vol 177, 1972 p16 SFF. 142/nonsense. Remember that, even if minutely, your watch is running slower. Your body had more mass, and, if you stand facing the cockpit, you are thinner. According to the special theory of relativity, a moving object appears to contract in the direction of motion as its velocity increases. James Terrell, a physicist, has demonstrated mathematically that this phenomenon is something like a visual illusion, and, in fact, is analogous to a projection of the real world onto the wall of Plato's cave. 6. Plato's famous parable of the cave describes a group of People who are chained inside a cave in such a way that they can see only the shadows on the wall of the cave. These shadows are the only world that these people know. One day, one of these people escapes into the world outside the cave. At first he is blinded by the sunlight, but when he recovers, he realizes that this is the real world, and what he previously considered to be the real world was, in fact, only the projection of the real world onto the wall of the cave. Unfortunately, when he returned to the people who still were chained inside the cave, they thought he was mad. Figure depicts a view looking down on the top of our head and the top of a sphere. The lines connect our eyes with points on either side of the sphere. If we are far enough away from the sphere, the distance between these points is almost equal to the diameter of the sphere. Figure is drawn as if the artist were looking down on the top of our head, our eyes, and the sphere. Special nonsense /143. The first step in Terrell's explanation is to draw lines downward, back into the page, from each of the 2 points on the sphere to a screen diagonal below the sphere. Figure B is a side view showing the 2 points, the lines that we have drawn downward, and the screen. If thou hold this book directly in front of you, your eyes are in the same position relative to the dotted lines as the eyes drawn in figure A. To understand Terrell's explanation, suppose that the sphere is moving very fast relative to the speed of light from right to left. If the sphere moves fast enough, some very interesting things happen. For example, before the light from the point on the far left edge of the sphere can reach us, the ball moves in front of it, blocking it from our vision. The reverse happens. On the far right, the ball moves out from between us and the light signals originating from points that used to be on the back side of the ball. These signals now are visible to us, while the signals coming from the point that used to be on the leading edge of the ball now are blocked by the ball itself as it moves to the left. The effect of this is an illusion of sorts. What we see is the same thing that we would see if someone had rotated the ball around its axis. Look what happened to the distance between the 2 points. As projected on the screen, it is considerably less than when we started the equations in the special theory of relativity. The Lorentz transformations, which show a contraction due to motion, describe these projections. Is this beginning to sound like Plato's cave? The fact that the ball, by moving fast enough, gets in the way of some of its own light signals and out of the way of others causes the ball to appear to rotate. This causes the projected distance between any 2 points on it which are aligned with the direction of motion to decrease, just as if someone really had rotated the ball. The faster the ball moves, the more it appears to rotate, and the closer together come the points projected on the screen. It is the projection that contracts instead of screen. Substitute view of the ball from our frame of reference, and we have the Terrell explanation of relativistic contraction. As yet, no analogous explanations have been found for the time dilation that accompanies moving clocks or the increase of mass that accompanies moving objects, but the effort, relatively speaking, is young. 144/nonsense. The special theory of relativity shows the mass of a moving object increases as the velocity of the object increases. Newton would not have hesitated to call this nonsense, but then Newton's experience was limited to velocities that are quite slow compared to the speed of light. Classical physics tells us that a specific amount of force is required to increase the velocity of a moving object by a given amount, for example, 1 foot per second. Once we know what that amount of force is, whenever we want to increase the velocity of that particular object by 1 foot per second, all we need do is apply that amount of force to it. If the object has a velocity of 100 feet per second, that specific amount of force will increase its velocity to 101 feet per second. According to Newton's physics, the same amount of force that increases the velocity of an object from 100 feet per second to 101 feet per second also will increase the velocity of the same object from 8,000 feet per second to 8,001 feet per second. The problem is that Newtonian physics is wrong. It takes much more force to increase by 1 foot per second the velocity of an object moving at 8,000 feet per second than it takes to increase by 1 foot per second the velocity of the same object moving at 100 feet per second. That is because a faster moving object has more kinetic energy of motion. This additional energy makes it behave exactly as if it had more mass. A given amount of force applied for a given amount of time will accelerate a single freight car to a greater velocity than the same amount of force applied for the same amount of time to an entire train. Of course, this is because an entire tram has more mass than a single car. When particles travel at velocities that are fast relative to the speed of light, their high kinetic energy makes them behave as though they have more mass than they have at lower velocities. In fact, the special theory of relativity shows that the effective mass of a moving object does increase with velocity. Since most subatomic particles travel at different velocities, each one of them can have many different relative masses. Therefore, physicists have calculated the rest mass of each particle. The rest mass of a subatomic particle is its mass when it is not moving. Subatomic particles are never really at rest, but these calculations provide a uniform method of comparing their masses. This is necessary since, as the velocity of special nonsense /145, a particle approaches the speed of light, its relative mass depends upon how fast it is moving. Einstein's discovery that moving clocks change their rhythm led to some spectacular revisions in the way that we see the world. It showed that there is no universal time that meets the universe. There are only proper times associated with various observers. The proper time of each observer is different, unless two of them happen to be at rest relative to each other. If the universe has a heartbeat, its rate depends upon the hearer. The special theory of relativity shows that two events which happen at the same time in one frame of reference may occur at different times when seen from another frame of reference. To illustrate this point, Einstein used one of his famous thought experiments. A thought experiment is a mental exercise. It has the advantage of requiring no apparatus other than that mind, which frees it from the practical limitations of laboratory experiments. Most physicists accept the use of thought experiments as a valid theoretical tool, provided they are satisfied that if the experiment could be performed, the results of the actual experiment would be the same as those of the thought experiment. Suppose that we are in a moving room. The room is moving with a uniform velocity. Exactly in the center of the room is a light bulb which flashes pendicular. The room is made of glass so that an outside observer can see what happens inside. At the precise moment that we pass an outside observer, The light flashes. The question is there any difference between what we see inside the moving room and what the outside observer sees according to the special theory of relativity? The answer is an extraordinary, concept-shattering yes, there is a big difference. Inside the room, we see the bulb flash and we see the light spread out in all directions at the same speed. Since the walls of the room are equidistant from the bulb, we see the light strike the forward wall and rearward wall of the room simultaneously. The outside observer also sees the flash, and he also sees the light propagate in all directions at the same speed. However, in addition, he sees that the room is moving from his 146 /nonsense point of view. The forward wall tries to escape the approaching light while the rearward wall rushes to meet it. To the outside observer, the light reaches the rearward wall before it reaches the forward wall. If the speed of the room is small compared to the speed of light, the light reaches the rearward wall only slightly ahead of the forward wall. Nonetheless, the light reaches the rearward and forward walls in a 1-2 order, and not at the same time. Although both of us observed the same two events, the light striking the forward wall and the light striking the rearward wall, we each have different stories to tell to us inside the room. The two events were simultaneous to the outside observer. One event came first and the other event came later. Einstein's revolutionary insight was that events which are simultaneous for one observer may occur at different times for another observer depending upon their relative motion. Put another way, two events, one of which occurs before the other, as seen from the frame of reference of one observer, may occur at the same time when seen from the frame of reference of another observer. One observer uses the word sooner, and later the other observer uses the word simultaneous, even though both of them are describing the same two events. In other words, sooner, later, and simultaneous are local terms. They have no meaning in the universe at large, unless they are tied down to a specific frame of reference. What is sooner in one frame of reference may be later in another frame of reference and simultaneous in a third. The mathematics which translate what an observer in one frame of reference sees into what an observer in another frame of reference sees are the Lorentz transformations. Einstein adopted the Lorentz transformations, which are a set of equations, virtually intact. No one before Einstein got these startling results from this simple type of thought experiment because no one before Einstein had the audacity to postulate something as outrageous as the principle of the constancy of the velocity of light. No one had the audacity to postulate something as outrageous as the principle of the constancy of the velocity of light, because the principle of the constancy of the velocity this is only true for events that are space-like separated. For time-like separated events, the relation earlier-later is preserved. For all observers time-like separated events can never appear simultaneous in any frame of reference moving with a velocity less than c. Space-like separation is explained later. Special nonsense /147 of light completely and unequivocally contradicts common sense, specifically, common sense as represented by the classical transformation laws. The classical transformation laws are so embedded in our everyday experience that it simply never occurred to anybody to question them. Even when the Michelson-Morley experiment produced results that were incompatible with the classical transformation laws, no beginner's mind but Einstein's conceived that the classical transformation laws might be wrong. Only Einstein suspected that at very high velocities far faster than those that we encounter through our senses, the classical transformation laws do not apply. This is not to say that they are incorrect at low velocities, compared to 186,000 miles per second. Contraction and time dilation are not detectable sensibly in this limited situation. The classical transformations are a good guide for practical experience. After all, we do reach the top of an escalator faster if we walk. If we do the moving room experiment with sound instead of light, we do not get the special theory of relativity. We get a confirmation of the classical transformation laws. There is no principle of the constancy of the velocity of sound because the velocity of sound is not constant. It varies depending upon the motion of the observer, hearer, as dictated by common sense. The important word here is dictated. We live out our lives in a limited situation of low velocities, where the speed of sound, about 700 miles per hour, seems fast. Therefore our common sense is based upon our experiences in this limited environment. If we want to expand our understanding beyond the limitations of this environment, it is necessary to drastically rearrange our conceptual constructs. This is what Einstein did. He was the first person to see that this is what had to be done in order to make sense of such impossible experimental findings as the constancy of the velocity of light for each and every person who measures it, regardless of their states of motion. This led him to turn the puzzle of the constancy of the velocity of light into the principle of the constancy of the velocity of light. In turn, that led him to the conclusion that if the velocity of light really is constant for all observers, then the measuring instruments used by different observers in different states of motion somehow must vary so that all of them give the same result. By a stroke of luck, Einstein discovered that these same variances were expressed in the equations of 148/nonsense. The Dutch physicist, Henk Lorentz, and so he borrowed them. Lastly, the fact that moving clocks change their rhythm led Einstein to the inescapable conclusion that now, sooner, later, and simultaneous are relative terms. They all depend upon the state of motion of the observer. This conclusion is precisely the opposite of the assumption upon which Newtonian physics is based. Newton assumed, as did we all, that there is one clock ticking off the seconds by which the entire universe grows older for every second of time that passes in this corner of the universe. 1 second of time passes also in every other corner of the universe. According to Einstein, this is incorrect. How can anyone say when it is now throughout the universe? If we try to designate now by the occurrence of two simultaneous events, like MV arrival at the doctor's office and my watch indicating 3 o'clock, we find that an observer in another frame of reference sees one of our events happening before the other. Absolute time, wrote Newton, flows equably, but he was wrong. There is no single time which flows equably for all observers. There is no absolute time. The existence of one ultimate flow of time throughout the physical universe, which we all tacitly acknowledged, turned out to be another piece of clothing that the emperor wasn't wearing. Newton made one more mistake in this regard. He said that time and space were separate. According to Einstein, time and space are not separate. Something cannot exist at some place without existing at some time, and neither can it exist at some time without existing at some place. Most of us think of space and time as separate because that is the way that we think that we experience them. For example, we seem to have some control over our position in space, but none at all over our position in time. There is nothing that we can do about the flow of time. We can choose to stand perfectly still, in which case our position in space does not change, but there is no way that we can stand still in time. This notwithstanding, there is something very elusive about space and especially about time, something that prevents us from resting our accounts with them prematurely. Subjectively, time has a fluid quality which much resembles a running brook, sometimes bubbling past in a furious rush, sometimes slipping by quietly unnoticed, and sometimes lying special nonsense /149. Languid, almost stationary, in deep pools. Space, too, has an ubiquitous quality about it which belies the common notion that it's /s only to separate things. William Blake's famous pot in eye cashes out toward these intangible qualities. To see a what idma, one me of sand, and a to /en in av /ild one loe /ei. Hold infinity in the palm of your hand, and eternity in an hue. Its title BV no coincidence, is Organs of Innocence. The special theory of relativity is a physical theory. Its concern is with the mathematically calculable nature of reality. It is not a theory of subjectivity, although it shows that the appearances of physical reality may vary from one frame of reference to another. It is a theory about the unchanging, physicists' savant aspect of physical reality. Nonetheless, the special theory of relativity was the first mathematically rigorous physical theory to explore areas whose expression previously had been the domain of poets. Like any concise and poignant representation of reality, the theories of relativity are poetry to mathematicians and physicists. However, Albert Einstein's enormous public renown perhaps was due in part to a shared intuition that he had something profoundly relevant to say about space and time. What Einstein had to say about space and time is that there is no such thing as space and time. There is only space. Space-time is a continuum. A continuum is something whose parts are so close together, so arbitrarily small, that the continuum really cannot be broken down into them. There are no breaks in a continuum. It is called a continuum because it flows continuously. For example, a one-dimensional continuum is a line drawn on a wall. Theoretically, we might say that the line is comprised of a series of points, but the points are each infinitely close to one another. The result is that the line flows continuously from one end of it to the other. An example of a two-dimensional continuum is the wall. It has two dimensions, length and width. Similarly, all of the points on the wall are in contact with other points on the wall, and the wall itself is a continuous surface. A three-dimensional continuum is what we commonly call 150 /nonsense. Space. A pilot is flying his airplane, navigates in a three-dimensional continuum. To give his location, he must state, for example, not only how far north and how far east of a given point he is, but he also must report his altitude. The airplane itself, like all things physical, is three-dimensional. It has a width, a height and a depth. This is WHV mathematicians call our reality, the reality, too, three-dimensional. According to Newtonian physics, our three-dimensional reality is separate from, and mo/s forward in, a one-dimensional time. Not so, saves the special theory of relativity. Our reality is four-dimensional, and the fourth dimension is time. We live, breathe, and exist in a four-dimensional space. Time continuum. The Newtonian view of space and time is a dynamic picture. Events develop with the passage of time is one-dimensional and moves forward. The past, present, and future happen in that the special theory of relativity, however, saves that it is preferable, and more useful, to think in terms of a static, non-moving picture of space and this is the space-time continuum. In this static picture, the space-time continuum, events do not develop, they just are. If we could view our reality in a four-dimensional wave, we would see that everything that now seems to unfold before us with the passing of time, already exists in toto, painted, as it were, on the fabric of space-time. We would see all the past, the present, and the future with one glance. Of course, this is only a mathematical proposition, isn't it? Don't worry about visually /mg a four-dimensional world. Physicists can't do it either for the moment. Just assume that Einstein might be right, since the evidence so far suggests that he is. His message is that space and time are related in an intimate manner, for lack of a better way of saying it. He expressed this relationship by calling time a fourth dimension. Fourth dimension is a translation from one language to another. The original language is mathematics and the second language is English. The problem is that there is simply no way of precisely expressing what the first language saves in terms of the second language. Therefore, time as a fourth dimension is merely a label that we give to a relationship. The relationship in question is the relationship between space and time as it is expressed mathematically in the theories of relativity. Special nonsense /151. The relationship between space and time that Einstein discovered is similar to the relationship between the sides of a right triangle which Pythagoras, the Greek, a contemporary of Confucius, discovered about 550 B. A right triangle is a triangle that contains a right angle. A NGHT angle is formed whenever two perpendicular lines intersect. Below is a right triangle. The side of a right triangle that is opposite the right angle is called the hypotenuse, hypotenuse. The hypotenuse is always the longest side of a right triangle. Pythagoras discovered that as long as we know the length of the two shorter sides of a right triangle, we can calculate the length of the longest side. This relationship, expressed mathematically, is the Pythagorean theorem. The first leg squared plus the second leg squared equals the hypotenuse squared. A hypotenuse of a given length can be calculated from different combinations of shorter legs. In other words, there are many combinations of different psi/e legs that all calculate to have the same hypotenuse. Hypotenuse leg, right angle leg. For example, the first leg might be very short and the second leg very long. 152 / nonsense. Or the other way round. BC. Or anything in between. Hypotenuse. If we substitute space for one of the legs of a right triangle, time for the other leg, and space-time interval for the hypotenuse, we have a relationship which is conceptually anal. owes to the relationship between space, time, and the space time interval described in the special theory of relativity. The Pythagorean theorem is C2 equals A2 plus I2. The equation for the space-time interval in the special theory of relativity is S2 equals T2x2. The Pythagorean theorem describes properties in Euclidean space. The equation for the space-time interval describes properties in Minkowski's flat space-time, Euclidean and non-Euclidean space are discussed in the next chapter. There are other differences as well, but the fundamental relationship between space, time, and the space-time interval is very similar to the relationship expressed in the Pythagorean theorem between the three sides of a right triangle. Special nonsense /153. Space-time interval between two events is an absolute. It never varies. It can appear differently to observers in different states of motion, but it is, itself, invariant. The special theory of relativity shows how observers in different frames of reference can observe the same two events and calculate the space-time. The fundamental invariant space-time view of much space and little time. The variables space and time view of much time and little space interval between them. The answer that all of the observers get will be the same. One observer may be in a state of motion such that for him there is a time and a distance involved between the two events, and another observer may be in a state of motion such that his measuring devices indicate a different distance and a different time between the events, but the space-time interval between the two events does not vary. For example, the space-time interval, the absolute separation between two exploding stars, is the same whether it is viewed from a slow moving frame of reference like a planet, or from a fast-moving frame of reference, like a speeding rocket. Let us return to our experiment with the moving glass room. Although we inside the room saw the light strike the rearward and forward walls simultaneously, the outside observer saw the light strike the rearward wall before it reached the forward wall. Nevertheless, by using a Pythagorean-like equation, into which we and the outside observer feed our time and thanks to Guy Murchie, who drew the original version of this drawing in his fine book, Music of the Spheres, New York, Dover, 1961. 154/nonsense. Distance measurements, we both get the same space-time interval between the events. Actually, this Pythagorean-like relationship was the discovery of Einstein's mathematics teacher, Hermann Minkowski, who was inspired by his most famous student's special theory of relativity. In 1908, Minkowski announced his vision this way: henceforth space by itself, and time BV itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. 8. Minkowski's mathematical explorations of space and time were both revolutionary and fascinating. Out of them came a simple diagram of space-time showing the mathematical relationship of the past, present, and the future of the wealth of information contained in this diagram. The most striking is that all of the past and all of the future for each individual meet and forever meet, at one single point. Now further more, the now of each individual is specifically located, and will never be found in any other place than here, wherever the observer is at. 63 years before Ram Dass's great book, Be Here Now, established the watchwords of the awareness movement. Hermann Mikulski proved that, in physical reality, no choice exists in the matter, pun, unfortunately for physicists, the realization is not always the experience nonetheless, after 2000 years of use in the East, being here now. The beginning step in meditation received the validation of Western science via Mikulski's rigorous mathematical confirmation of it inspired BV the special theory of relativity. The last and the most famous aspect of the special theory of relativity is the revelation that mass is a form of energy, and that energy has mass. In Einstein's words, energy has mass, and mass represents energy 9. Although this sounds shocking in one sense, in the sense that we have believed ever so long that matter, stuff is different from energy just as the body is different from the mind, another form of the same theory. In another sense, it sounds surprising, natural. The matter-energy dichotomy goes back at least as far as the Old Testament Genesis portrays man as a sort of ceramic creation. God scoops up a handful special nonsense /155 of clay, matter, and breathes life, energy, into it. The Old Testament is a product of the Western world, or the other way round. Physics also is a product of the Western world. In the East, however, there never has been much philosophical or religious, only in the West are these two separate. Confusion about matter and energy. The world of matter is a relative world, and an illusive one. Illusory not in the sense that it does not exist, but illusory in the sense that we do not see it as it really is. The way it really is cannot be communicated.